Hey guys, tonight I want to take you back to a world so ancient, so impossibly alive, that it will make everything you thought you knew about our planet feel like a half-remembered dream. Here is something that will stay with you. The Stegosaurus, that gentle armored giant with the famous bony plates running down its spine, went extinct nearly 80 million years before the Tyrannosaurus Rex was ever born. 80 million years. Let that settle for just a moment. The gap between Stegosaurus and T-Rex is wider than the gap between T-Rex and you. Sitting here tonight, listening to this, the Jurassic and the Cretaceous feel like one great age to us, pressed together into the word dinosaur, but they were separated by an ocean of time so vast that the creatures who lived on each shore of it would have been as foreign to one another as they are to us today. Welcome, I am glad you are here. Wherever you are in the world tonight, whether it is late and dark and quiet outside your window, or early morning before the light has decided what it wants to do, pull the covers a little closer. Let your shoulders drop. Let your jaw unclench. If you enjoy listening to sleepy, prehistoric dinosaur stories like this, subscribe. I post stories like this weekly, and there is always another ancient world waiting for you when you return. Tonight we are going back, all the way back, 150 million years, give or take, to a world that was green and warm and never once knew the word silence. A world of enormous shadows and distant rivers and slow-moving giants and creatures so vast they shook the ground simply by breathing. The world we are entering is not the world of terrifying monsters that you might have learned about as a child, though some of its inhabitants are extraordinary in their scale. It is, above all, a world at rest, a world moving at the pace of deep time, where the same fern has grown in the same wet hollow for 10,000 years, where the same river has carried the same red silt toward the same distant sea for longer than any mind can hold. A world in which the extraordinary is simply the ordinary, repeated without urgency across geological ages. Let your breathing slow. Let the sounds of wherever you are tonight begin to fall back, gently, behind the sounds of a place that existed long before anyone was there to name it. Come, rest, let it begin. The world is not yet light. You are somewhere in the middle of what will one day be called North America, though no human mind exists yet to give it that name, and the land beneath you bears no resemblance to anything that word will ever come to mean. The year, if you could count it, is approximately 153 million years ago. The continent is still in the slow business of becoming itself. The old supercontinent Pangaea, having spent tens of millions of years pulling apart like warm bread, the pieces drifting on plates of rock so massive they move at the speed of a growing fingernail. The sea that will eventually become the Atlantic Ocean is still a young thing, narrow and shallow, not yet convinced of its own permanence. The mountains to the west are younger than they look, still lifting, still finding their height in the slow conversation between crustal plates that never stops and never hurries. You rest on a long slope of ground that angles gently toward a distant floodplain you cannot quite see in the dark. The grasses you might expect beneath you are absent. There is no grass here. Grass is still more than 100 million years in the future. An evolutionary experiment not yet conceived, not yet necessary. What lies beneath you is a deep mat of fallen conifer needles, dark and softened by time, pressed into layers by decades of rain and sun and rain again. It gives slightly under your weight. It smells like something between earth and spice, like a forest floor after rain, but older, denser, more saturated with geological time. This smell has no name because no language has yet been invented to name it. It simply is. It simply exists in the absolute way that only the very old can exist, with a certainty that has outlasted every reason to doubt itself. The air above you is warm, not uncomfortably so, but warm in the way that a room feels when a fire has been burning for many hours, and the stones of the hearth have taken the heat deep into themselves and are giving it back slowly into the night. The Jurassic world runs several degrees warmer than the world you know. This is one of the facts that becomes more extraordinary the longer you sit with it. There are no ice caps at either pole. The poles themselves are forested, temperate, dark for long stretches of the year, but never truly frozen. The equatorial zones are not the parched deserts of some warmer future, but lush, rain-soaked realms where growth is the only law that matters. The whole planet exhales warmth the way a sleeping body does. From every surface, at every hour, an enormous living thermostat set several degrees higher than the one you have always known. The sky above you is clearing. For the past several weeks, this region has been under the influence of a seasonal monsoon drawn inland from the great seaway that lies to the east. And the ground still holds the memory of that water in every depression, every hollow, every low place between the roots of the trees that surround you on three sides. But the monsoon is withdrawing now, pulling back toward the coast the way a tide pulls back. And the sky that remains behind it is extraordinarily clear. The stars, when they appear through the last dissolving fragments of cloud, are the same stars that will shine above every human life ever lived, though no human has yet had the experience of looking up at them and feeling wonder. They are simply present tonight, vast and cold and indifferent to the warm world beneath them, as they have been present for longer than the planet itself has existed. You can hear the forest before you can see it. There is a sound that has no exact parallel in the world, you know. A layered, continuous sound that builds itself from 100 smaller sounds until it becomes something larger than any of its parts. Insects not the buzz of bees, because bees do not yet exist in this period. The long relationship between flower and bee not yet invented, because flowers themselves have not yet been invented. Instead, the sound is a rasping, a clicking, a low stridulation from creatures that are evolving rapidly toward crickets and katydids and cicadas, but are not quite any of those things yet. The clicking of beetles deep inside fallen wood, the persistent low churring of something large moving through the fern understory 30 meters to your left, something you cannot see, something that stops and starts and then stops again in the particular way of a creature that is listening as hard as it is moving. Then beneath the insects, water, a stream nearby, running shallow and clear over stones that have been polished by 10,000 years of similar water, carrying fine traces of red iron oxide that stain the stone a color between rust and clay. The stream talks to itself in the way that fast, shallow water always does, not loudly, but with a kind of constant, soft insistence, a voice that has been speaking for centuries and expects to go on speaking for centuries more, unhurried by any audience, unbothered by any silence. And beneath the water, beneath even that, you become aware of a sound so low it is more felt than heard. A vibration in the earth beneath your mat of fallen needles, a deep, periodic tremor in the ground, like a very slow heartbeat belonging to something very large. It pauses. It comes again. It is steady without being mechanical, organic without being hurried. You do not know yet what is making it, but we will come to that. The sky above the eastern ridge is beginning to change. The deep blue of night is softening at its lowest edge, taking on the color of something that is not quite blue and not quite grey, that particular threshold between dark and dawn that different languages have tried to name in different ways, and none has quite managed. The first bird things are beginning to stir in the upper canopy. They are not birds, not exactly, not yet. Some of them belong to the genus Archaeopteryx, those extraordinary creatures that stand precisely on the evolutionary border between the theropod dinosaur they descended from and the bird they are in the slow process of becoming. Others are related but distinct, small feathered theropods that roost in the conifers and emit sounds that are more reptilian rasp than birdsong, though there is something in the variation of those calls, something in the pattern of call and response between the trees that suggests a kind of meaning is being exchanged that we will never fully decode. The forest around you is a conifer forest, but not a forest you would recognize by that name. The trees here include no pines, no spruces, no firs that you would know. These are older lineages, Araucarian conifers with upswept branches and dark, scale-like leaves. Ancestors of the trees still surviving today in the mountains of Chile and the hillsides of New Caledonia. Their bark is thick and deeply furrowed. Their roots have been in this soil for so long that the soil has shaped itself around them, grown into their angles, become part of their architecture. Between them grow the cycads, ancient plants with thick trunks and feathery crowns that look like a cross between a palm tree and a fern, though they are neither, having split off from both lines before either line had fully formed. They grow slowly, these cycads, some of them taking a century to reach shoulder height, and they will outlast everything in this forest by geological margins. The ferns are everywhere. They carpet the ground between the trees in shade-loving mats of deep green. They grow from the joints of fallen logs in cascading clusters. They climb the damp north-facing sides of boulders. In the wetter hollows they reach shoulder height or higher, the fronds so dense and overlapping that moving through them would be like pushing through a green curtain. There are no flowering plants here. No roses, no daisies, no grasses, no broad-leafed shrubs with petals and nectar and the complicated reproductive machinery of flowers. All of that is still 100 million years away, still waiting for the right moment in the right evolutionary lineage to appear and change everything. This forest is older than flowers. It smells like rain and resin and the slow decay of fallen wood, a smell of enormous age and enormous patience. As the sky continues to lighten in the east, the forest floor begins to emerge from darkness with a slowness that feels deliberate. First, the shapes of tree roots, enormous buttressing curves of wood that sweep up from the needle-covered ground. Then, the pale undersides of the lowest fern fronds, catching the first grey light and holding it. Then, the trunks themselves, darker against the lighter sky to the east, vertical lines that organize the horizontal world of the ground into something navigable. The vibration in the ground comes again, closer perhaps. Or perhaps you are simply more attuned to it now that the world has grown slightly lighter and your other senses have relaxed slightly in response. Something very large is moving, somewhere not far to the north of you, moving slowly, moving without urgency, in the unhurried way of a creature that has no predators capable of surprising it, a creature large enough that the earth itself must yield when it walks. The footfalls come irregularly, not in the even rhythm of something running or frightened, but in the ambling, weighted rhythm of a grazing animal that stops and feeds and moves 3 steps and stops again. Each step sends a tremor through the ground that you can feel in your spine and in your palms where they rest on the needled earth. You do not need to see it to know that it is enormous. The Jurassic dawn continues its patient work around you, lightening degree by degree, bringing first grey, then the faintest greenish cast to the eastern sky, then something approaching pale gold above the ridge. The insects are louder now. The stream is unchanged, still talking to itself, still carrying its red-stained water toward the floodplain. The bird things in the canopy are more active, their calls overlapping in the way of creatures establishing territory against the clock of a morning they know will arrive, whether or not they have finished claiming their corner of it. The smell of the forest is stronger in the early morning, as it always is, as it will always be in every forest that ever grows on this planet. For as long as forests are a thing that this planet does, the night cools everything slightly, and the cooling releases the held scents of the day before, resin from the conifers, the slightly sour smell of decomposing plant matter in the wet hollows, something musky and warm from the direction of the vibrations, the body scent of an animal so large that its presence changes the air around it, the way a warm stone changes the air above it. You stay very still, not from fear, but from the kind of instinct that comes with witnessing something that you understand, even without words, should not be interrupted. The morning is happening. The Jurassic world is going about its ancient business. And for now, in this cool and humming and impossibly old dawn, you are simply here for it. A silent presence in a world that predates your existence by more than any number you have ever been taught to use. The footfalls stop. Somewhere in the half-dark of the northern forest, the great animal has found something worth its attention, something worth pausing for. The ground goes still beneath you. The first true light of the Jurassic morning reaches the top of the conifers, and the needles turn gold. Something ancient and enormous exhales in the dark, and the world continues on its slow way, as it has for millions of years, and will for millions more. The sun has cleared the ridge now, fully committed to the day, and the forest has become a different world in the light. The darkness that made it vast and unknowable has been replaced by something else, something that is not quite familiarity but is at least legibility. You can see where you are, more or less. You can see the shape of the land beneath the trees, the long, slow dip toward the stream to your east, the slight rise to the west, where the conifers grow taller and more crowded. You can see the color of things, the dark umber of tree bark, the 3 different shades of green in the fern understory, the strange silvery undersides of the cycad fronds when the breeze turns them, and you can see the canopy. What the darkness had hidden, the morning now reveals. The canopy of a Jurassic forest is not one single surface. It is a series of surfaces, layered one above the other, like the pages of a book that has swollen from water, each layer slightly different from the one above it and the one below. The highest layer belongs to the tallest Archaeopteryx conifers, trees that have been growing for a century or two and have had time to reach the light that all trees want. Their upper branches spread broadly, flattened by decades of wind into horizontal planes that are simultaneously reaching for sun and offering the least possible resistance to the storms that come through seasonally. Below them, the younger conifers and the tree ferns reach upward at angles, filling the gaps in the upper canopy, catching whatever light filters through. And below them, the understory of cycads and lower ferns and thick-stemmed horsetails forms a third world entirely, one of deep shade and high humidity and the slow drip of condensation from the layers above. What this canopy does not contain is flowers. Not a single petal, not a single nectar-filled cup waiting for a pollinator. The Jurassic forest is a world without that particular kind of color, without that particular kind of partnership between plant and insect that will eventually become one of the most productive evolutionary arrangements ever devised. Here, pollination happens differently. The conifers send their pollen on the wind, enormous clouds of yellow-green dust that drift between the trees for days after a dry spell, settling on everything, coloring the still pools at the stream's edge a soft yellow-green. It is an inefficient system in many ways, a scatter approach, an enormous investment of pollen for an uncertain outcome, but it has worked for these trees for hundreds of millions of years, and they show no interest in changing it. The cycads take a different approach. They are pollinated by beetles, primarily, and by a few other insects that are drawn to the scent their cones produce, a scent that is warm and slightly chemical, and not entirely pleasant by human standards, but evidently irresistible to the insects that have evolved to respond to it. The beetles crawl into the cones, gather pollen on their bodies, and carry it to the next cone. And in this way, the cycads have the beginning of what will one day become the flower-pollinator relationship, though neither the cycads nor the beetles know this, and neither of them is working toward any particular future. They are simply doing what they do. Here is something worth sitting with. The beetles that crawl through the cycad cones this morning are, in their general form and habit, not dramatically different from beetles you could find today in the bark of a fallen log. Beetles are one of the oldest success stories in the history of complex life on Earth. They appeared long before the Jurassic, and they will outlast the Jurassic by an interval that makes the Jurassic itself seem brief. If you were to pick up a small brown beetle from the needle-covered ground beside you this morning, it would feel in your hand like something ancient and also like something perfectly ordinary. Both of those feelings would be accurate. The forest is busy with beetles this morning. You can hear them in the wood if you hold still, and listen past the stream and the insect chorus and the distant footfalls that have resumed to the north. A clicking and a rasping and a low vibration in dead logs that tells you something is moving inside the wood, tunneling through the soft interior of a fallen conifer that has been on the ground long enough to have become more habitat than tree. The larvae of wood-boring beetles are at work in there, moving through channels they have excavated over months or years, consuming the cellulose that the tree spent its entire life building. When they are finished, the log will be a hollow shell and the wood will have passed back into the soil and eventually into the roots of another tree. Nothing is wasted here, nothing is lost. Everything is transformed at a pace that makes human urgency seem faintly comic. The temperature is rising now that the sun has fully arrived. Not quickly, not dramatically, but steadily in the way of a warm day that knows it has time. The resin smell from the conifers intensifies as the bark warms and the resins liquefy slightly and send their sharp, clean scent into the air. This is the smell of defense, primarily. The resins deter insects that would otherwise bore through the bark to reach the wood beneath. They seal wounds where branches have broken or bark has been scraped away. And sometimes, when a small insect lands on a drop of fresh resin, it becomes encased in it, preserved with a perfection that bone and shell and even teeth rarely achieve. Some of these resin drops will harden over centuries into amber, and some of that amber will endure for 150 million years. And when it is eventually found and opened, it will contain perfectly preserved beetles and flies and spiders, and fragments of plant that will tell the scientists who study them exactly what this morning looked like. The forest is writing its own record, in amber and in stone and in the sediment of the streams, a record that will take as long to read as it took to write. The ferns in the understory have released their morning dew. Each frond holds its drops briefly in the early light before the warmth coaxes them to let go, and they fall through layers of frond and needle to the ground below, adding their small sound to the general sound of water that this forest produces at every hour. Ferns have been part of this world for far longer than the conifers above them. They are extraordinarily ancient plants, going back to before the dinosaurs, before the first reptiles, to a time when the land was first being colonized by plants, and everything was an experiment, and survival was the only measure of success. The ferns that grow here today are not the same species as those earliest land plants, but they carry that ancient lineage in their biology, in the way they reproduce by spores rather than seeds, in the way their fronds uncurl from a tight fist into an open hand, a motion so characteristic it has its own name, circinate vernation, the slow uncoiling of something old. There are tree ferns here too, a fact worth pausing over. Tree ferns are not trees in the way that the conifers around you are trees. They do not have true wood. They grow by adding layers of fibrous stem material, not by laying down rings of dense heartwood. But they grow tall, some of them reaching 10 or 15 meters, their crowns of feathery fronds spreading above the understory canopy and creating their own small worlds of shade beneath them. Under a large tree fern, the light is filtered through several layers of frond, and the air is several degrees cooler than in the open. It smells strongly of growing things, of the chemical conversation that plants conduct constantly through volatile compounds released into the air, a conversation that has no sender and no receiver and no message that any language has yet learned to translate. Something lands on your arm. You look at it. It is an insect, a dragonfly-like creature with wings that span perhaps 15 centimeters, wings of extraordinary transparency, each one a network of veins, so fine they might have been drawn by the most patient hand imaginable. It sits with its wings held at an angle, warming them in the morning sun that falls through a gap in the canopy. It shows no awareness of you, or if it does, no concern. Its compound eyes, enormous in proportion to its head, reflect the light in tiny fractured repetitions of the world around you. After a moment it lifts and is gone, moving between the fern fronds at a speed that the eye cannot follow. Dragonflies are among the oldest flying insects on Earth. Their lineage goes back to before the Jurassic, to long before the first dinosaur took a step, to a time when the world's forests were made of enormous scale trees and giant club mosses, and the air was so oxygen-rich that insects could grow to extraordinary sizes. The dragonflies of the Carboniferous period, nearly 200 million years before this morning, had wingspans approaching 70 centimeters, the size of a modern hawk. The descendants in this Jurassic forest are smaller, more refined, optimized by millions of generations of flight into something more efficient than their enormous ancestors. But the basic design has not changed. The compound eyes, the transparent wings, the four-winged configuration that provides maneuverability in 3 dimensions that no bird will ever match. The dragonfly design worked so well, so early, that life has not seen any reason to substantially revise it in the 250 million years since it first appeared. You watch the gap in the canopy where the dragonfly disappeared. Other things are moving up there. Insects too small to identify from here, darting between shafts of light. A small lizard-like creature running along the underside of a branch with a sureness that tells you its feet have specialized surfaces, something adhesive that lets it treat vertical bark as though it were flat ground. There are many such small animals in this forest, animals that live their entire lives in the canopy and rarely if ever touch the ground, animals that have evolved to exploit the particular resources of the upper forest, in the way that species always evolve to exploit whatever is available and unoccupied. One of the conifers near you has a wound in its bark, a place where something has scraped away the outer layers, perhaps a large animal rubbing against it, perhaps lightning striking it in a past storm. From this wound, a long amber bead of resin has been flowing for weeks, building up in a thickening drop at the wound's lowest point. A small moth, or something moth-like, has landed in it. The moth's wings are pressed to its sides by the resin, which has already begun to harden slightly in the warmth of the morning. The moth will not escape. It will become part of the resin, and the resin will harden over the months and years ahead, and the amber will endure long after the tree that produced it, and the forest that surrounded it and the entire ecosystem of this morning have passed out of existence. And in this way, one small moth will be preserved for a time so long that the word eternal does not seem too large for it. The breeze that has been moving through the upper canopy all morning stirs the lower ferns now, a slightly cooler breath that comes and goes, that finds the gap in the trees to the east and moves through it for a moment before losing itself in the denser growth to the west. The ferns respond to it the way water responds to wind, not by resisting but by yielding completely and then returning exactly to where they were, as though the movement never happened. This is one of the fern's underrated qualities. It gives without breaking. It moves without going anywhere. The forest is fully awake now, if forests can be said to wake. The insect chorus has reached its daytime level and will not vary much until the temperature drops in the evening. The small creatures in the canopy are fully occupied. The stream to the east is unchanged, and will be unchanged at noon and at sunset and at midnight and tomorrow morning. The deep vibration from the north has resumed, steady and unhurried, moving slightly eastward now, tracking some food source or water source that only the enormous animal that produces it can sense. What is happening in this canopy this morning has been happening, with slight variations in its participants, for millions of years before this morning, and will go on happening, with more slight variations, for millions of years after. The Jurassic forest does not feel urgency. It does not feel anything, of course, in the way that you feel the warmth of the sun on your skin and the softness of the needles beneath your hands. But if it could feel, what it would feel is something like the deep satisfaction of a system working exactly as it should, a system so well calibrated by time and selection and patience that it has arrived at something very close to permanence. And in the warmth of this morning, in the smell of resin and fern and moving water, in the sound of the insects and the distant footfalls in the stream, you feel something of that permanence yourself, the sense that you have arrived, somehow, at a place that knows itself thoroughly, and that this knowing is restful in a way that very little else is. You breathe in. The forest smells like old certainty. You breathe out. Something enormous passes through the trees to the north, and the ground remembers its weight long after it has gone. If you are drifting now, let yourself go. The forest will still be here when you return. Subscribe so the next story is waiting when you wake. And sleep well. There are moments in the study of the natural world when numbers become almost useless, when the mind accepts a figure but refuses to translate it into something that can be felt. The weight of a Brachiosaurus is one of those moments. Estimates vary, because bones can only tell you so much and soft tissue leaves no lasting record. But a reasonably conservative guess puts a large adult Brachiosaurus at somewhere between 30 and 60 metric tons. 60 metric tons is the equivalent of approximately 8 or 9 fully grown African elephants standing on each other's shoulders, which is not a thing that happens and not a very useful image, but it is the best language offers when confronted with something this far outside normal scale. What the number cannot give you is the sound of it walking, and so we will begin there. You heard the vibration before you saw the animal. You have been hearing it for some time now, that low periodic tremor in the earth, like a heartbeat belonging to something that takes up more space than a heartbeat usually does. The animal has been moving east along the edge of the forest, following the line of a dry creek bed that floods in the monsoon season and provides reliable browse in the wet months, and it has rounded a long stand of tree ferns and come into view at a distance of perhaps 100 meters. The first thing you notice is the neck. The neck of a Brachiosaurus is genuinely difficult to look at without recalibrating everything you have assumed about what an animal can be. It extends upward and forward from the massive shoulders in a long, slightly curved line. Not vertical, but angled, the way a crane extends its arm. And at the end of it, at a height of approximately 9 or 10 meters above the ground, the small head moves slowly from side to side as the animal browses the upper canopy of the Archaeopteryx conifers. 9 meters, 3 stories above the ground. The head up there is surprisingly modest in size, narrow and rounded, with large dark eyes set on either side of a blunt snout. From where you sit, it looks almost delicate against the enormous architecture of the body below it. The body. The body is extraordinary in its plainness. It does not need ornament. It does not carry plates or horns or the elaborate display structures that some of its contemporaries will develop. It simply is massive, in the way that a mountain is massive, in the way that large bodies of still water are massive, with a kind of uncomplicated solidity that announces itself without any effort. The legs are columns, genuinely columnar in the architectural sense, thick and straight and set directly below the body's center of mass in the configuration that all the great sauropods share. The tail extends behind the body in a long, tapering sweep that adds another 15 or so meters to the animal's total length. At its end, the tail is thin as a rope. Here is something about that tail that the researchers who have studied it find quietly astonishing. The tail of Diplodocus, a close relative living in the same ecosystem and time, is so long and tapers so precisely toward its end that it could, in theory, be used like a bullwhip. The mathematics of such a tail suggest that its tip, if moved quickly enough through the right arc, would reach speeds exceeding the speed of sound, producing an audible crack not unlike a cannon shot. Whether any Diplodocus ever actually cracked its tail in this way is uncertain. Whether it did so for defense, for communication, for reasons we cannot currently guess, we cannot know. But the structure is there, the physics allow it, and it is a remarkable thing to contemplate that one of the quietest seeming animals of the Jurassic may have been capable of producing a sound that would have echoed off the canyon walls of the Morrison Formation for miles. The Brachiosaurus in front of you does not crack its tail. It stands with its weight distributed evenly across 4 pillar legs, its long neck moving slowly among the upper branches, its jaw working in steady side-to-side sweeps, as it strips needles and young growth from the Araucarian conifers with a mechanical patience that suggests an animal that has been eating for a long time and expects to go on eating for considerably longer. Its teeth are not designed for chewing. They are peg-like, thick and blunt, suited to stripping plant material rather than grinding it. The actual digestion of all that tough conifer growth happens later, in an enormous fermentation chamber of a stomach where bacteria do the slow chemical work of breaking down cellulose into something nutritional, and the heart. Let us pause on the heart, because the heart of a Brachiosaurus is one of the most extraordinary organs that any animal on Earth has ever carried. To pump blood from the chest all the way up a 10-meter neck to a brain 9 meters above the ground, a heart has to generate enormous pressure several times greater than the human heart at full exertion. The Brachiosaurus heart is estimated to have weighed in the neighborhood of 400 pounds. 400 pounds simply to move blood up a neck. It beats somewhere deep inside that enormous chest cavity, behind ribs as thick as the beams of a large building, and you cannot hear it from here, but you can feel the consequences of it in the sheer, impossible aliveness of the animal in front of you, the fact that it stands and breathes and moves and browses when everything about its size argues against existence. The respiratory system of large sauropods is another quiet marvel. Paleontologists who have studied the internal structure of sauropod vertebrae have found that they were honeycombed with air spaces, not solid bone as you might expect, but a lattice of chambers that connected to an extensive system of air sacs, the same kind of air sac system found in modern birds. This system works differently from the lungs of mammals, where a mammal's lungs fill and partially empty with each breath, meaning the air in them at any given moment is a mixture of fresh and already depleted oxygen. The air sac system of a bird lung arrangement means that air flows through the respiratory system in one direction, always fresh, always oxygenated. It is a more efficient system, and for an animal the size of a sauropod, efficiency in the respiratory system is not a luxury but an absolute necessity. The Brachiosaurus in front of you breathes with a kind of effortless perfection that its physiology has been working toward for tens of millions of years. There is a second Brachiosaurus further back in the trees. You can tell by the slight secondary vibration in the ground, slightly out of phase with the one produced by the animal you can see, the way 2 large bells slightly mistuned will produce a beat frequency between their separate sounds. The second animal does not emerge from the tree line. It is a juvenile, you will understand later, perhaps 3 or 4 years old, perhaps 15 meters long already, following its parent or parent figure through the forest with the same slow patience. The relationship between Jurassic sauropods and their young is something we understand only partially. Eggs have been found. The eggs are surprisingly small, roughly the size of a basketball, a fact that never fails to astonish when you hold the adult animal in your mind alongside it, that a creature which will eventually weigh 60 metric tons began its life in an object small enough to carry under one arm. The young sauropod grows fast. Studies of fossil bone growth rings, the same kind of growth rings you can read in a tree trunk, show that juvenile sauropods added mass at rates comparable to the fastest-growing large animals alive today. A Brachiosaurus may have reached something close to adult size within 20 or 30 years, then grown more slowly for decades after that, potentially living to an age of 80 or 100 years or more. This is long life by any reckoning. A century of slow movement through warm forests, a century of that steady vibration in the earth, a century of high browsing among the conifers as the world changed slowly around the animal, and the animal absorbed all of those changes at the same unhurried pace with which it did everything else. The adult Brachiosaurus has moved slightly closer while you were watching, not toward you with any intention. Simply moving along its browsing path, following the line of taller conifers, and the path has brought it to perhaps 60 meters. At this distance, the scale becomes something felt rather than calculated. The body blocks out a significant portion of the sky to the north. The footfalls, when they come, are not loud, but they are deep, a thud that goes through the soles of your feet rather than into your ears. The animal smells of warmth and old plant matter, and something musky and specific that you could not describe but would recognize immediately if you smelled it again. The head descends from its 9-meter browsing height. The Brachiosaurus is investigating something at a lower elevation, something among the young cycads at the edge of the tree line. The neck curves down in a long, slow arc that takes several seconds to complete, the whole enormous length of it flexing with the unhurried grace of something that has never needed to do anything quickly. The head reaches the cycad level and pauses. The jaw works. The animal lifts its head again, just slightly, and you can see it swallowing. Then the neck extends upward again, returning to its preferred browsing altitude, and the slow, rhythmic work of feeding resumes. Here is a thought that sits quietly but persistently in the mind. The trees that this Brachiosaurus is feeding on this morning have been growing for perhaps 150 years. The animal is perhaps 60 years old. The forest in which they both exist has been here, in some form, for millions of years, and the deep red rocks beneath the soil, the Morrison Formation rocks that are slowly accumulating layer by layer as seasonal floods deposit silt across the floodplain to the east. Those rocks will preserve the bones of this animal, and others like it for 150 million years, until the slow uplift of a future mountain range brings them close enough to the surface that the erosion of a different kind of rain eventually exposes them in the walls of canyons that do not yet exist in places that have not yet been named. The bones will be found. The bones will be studied. The creature in front of you will have a name, will have a genus and a species, and a place in a classification system that will take the efforts of thousands of careful people over many decades to develop and revise and argue about and gradually come to agree upon. It will be displayed in museums, reconstructed in images, described in books and films and stories. Children who have not yet been born, in cities that do not yet exist, on the soil of continents that are still forming from the pieces of a supercontinent that is still in the slow process of breaking apart. Those children will know this animal's name, will reach up to touch a cast of its femur, itself taller than the child and much of the wall behind it, will say the name out loud in the particular way that children say the names of things that astonish them. But all of that is very far from this morning. Here now, the Brachiosaurus simply eats. The second vibration, the juvenile one, has moved slightly east, following a water smell perhaps, or simply following the pattern of morning that a young sauropod is in the long, slow process of learning. The forest resettles around the animal's passing. The ferns that were displaced by a footfall nod back into position. The insect chorus, which paused briefly when the animal was very close, resumes its steady, indifferent sound. The adult pauses in its browsing. The head stills. The huge dark eye, visible from here as a dark oval against the paler skin of the face, seems to look at nothing in particular, or perhaps it is looking at everything, at the whole visible world registered simultaneously by those wide-set eyes that provide a field of view nothing with predatory forward-facing eyes could match. Then the neck swings gently back to the north, and the animal follows it, and the vibrations in the earth continue northward and diminish and are absorbed by the distance and the sound of the stream and the insect chorus and the quiet, patient work of the forest doing what forests do, which is to grow, without urgency, in the direction of the light. The afternoon heat has settled over the forest like something physical. It presses down through the canopy in slanted shafts of amber light, heating the upper fern fronds to warmth and sending the insects to the cooler air lower down, where they drift in slow, purposeful patterns between the stems. The stream has dropped slightly in the past week as the monsoon recedes, and the groundwater that feeds it follows the rain westward toward the coast. But it still runs. It will run for months yet, carrying its red-stained water in the unhurried way of a stream that has been doing this for a very long time and has no plans to stop. You become aware, gradually, of a stillness that is different from the usual stillness of the afternoon. The insects are present, the stream is present, but some threshold of noise that you had not consciously noticed has dropped. The small lizard-like animals that have been moving through the understory all morning have gone quiet, have gone somewhere, have removed themselves from the visible world with the particular decisiveness of small animals that have learned, generation by generation, to interpret certain signals in the environment as reasons to be elsewhere. The ferns to the north of you are still. Something is there. Not moving. Standing, perhaps, in the dense wall of fern fronds that blocks your view of the ground beyond the stream. Standing and being still in the way that only an animal that understands stillness as a tool can be still, utterly without fidget or adjustment, utterly committed to invisibility despite the enormous volume that a body of this size occupies. The Allosaurus emerges from the fern wall in the way that very large things sometimes move, with a slowness that is not hesitation but deliberateness. 1 foot placed, then the body following, then the other foot. It is perhaps 9 meters long, perhaps 2 metric tons in weight. Though those numbers do not adequately describe the experience of it, the experience of something that tall and that present moving through a space that is suddenly reconfigured around it. Its head is enormous, perhaps the most striking thing about it. A massive, wedge-shaped skull carried on a neck that is thick and muscular, but not long in the way of the sauropods, not built for browsing but for the different work of seeing and seizing. The skull is fenestrated, meaning it is not solid bone but a framework of bone surrounding large openings, a design that reduces weight without sacrificing structural strength, and this lightness of the skull is part of what makes the bite strategy of large theropods possible. A skull light enough to be swung with speed and precision, attached to jaw muscles powerful enough to make that speed meaningful. Here is a thing about the Allosaurus that was not understood until relatively recently. It is not as heavy as it looks. A 9-meter Allosaurus weighs approximately what a large bull elephant weighs, about 2 metric tons, because the bones are hollow in many places. Honeycombed with air spaces the way the bones of birds are hollow, a characteristic inherited from the theropod ancestry that Allosaurus shares with the birds that will eventually evolve from within this lineage. This means that the Allosaurus can move faster than its size suggests. It can accelerate. It can change direction with an agility that pure muscle mass would seem to prohibit. The hollow bones are not a compromise. They are an engineering solution to a problem that evolution solved very well, the problem of how to be large and fast simultaneously. The Allosaurus pauses at the edge of the stream. The water here is perhaps ankle deep on an animal of its height, which means perhaps 10 centimeters of water over flat stones. It lowers its head and drinks with a motion that is surprisingly efficient, unhurried. The jaw opens. Water goes in. The jaw closes. The throat moves. The head rises. You can see the water running from the lower jaw in small streams that catch the afternoon light. The eye, on the side of the head visible to you from here, is large and amber, with a vertical pupil that contracts slightly in the bright, stream-side light. It does not look at you. It looks at the middle distance upstream, where the stream bends around a stand of horsetails and disappears. Allosaurus was, by the measures available to us, the apex predator of the Morrison ecosystem. Not the only large predator, The Morrison was rich in predators, but the largest and perhaps the most successful. Fossils of Allosaurus have been found at more sites in the Morrison Formation than virtually any other large theropod. The Cleveland Lloyd Dinosaur Quarry in Utah, one of the most productive dinosaur fossil sites in the world, contains the bones of at least 46 individual Allosaurus individuals, more than all other dinosaur species at that site combined. Why so many Allosaurus bones in one place remains a question without a completely settled answer. One hypothesis is that the quarry represents a predator trap, a place where prey animals became mired in soft mud and were then followed by predators who also became mired, and so on, a slow accumulation of misfortune that preserved an unusual concentration of the ecosystem's top predators. 46 individuals. Standing in this forest this afternoon, watching one animal drink from a stream, it is useful to remember that this is a species, not an individual. Somewhere beyond the visible forest there are other Allosaurus, younger and older. Some of them moving through the same kind of afternoon, some of them resting, some hunting. The species is distributed across what will eventually be Utah and Colorado and Wyoming, and parts of several neighboring states. It has been in this ecosystem for millions of years, and will be here for millions more. It is not a rare thing, this animal at the stream. It is a working part of a system that depends on it. The role of the large predator in an ecosystem is often described in terms of destruction, of taking, of ending, but the more accurate description is one of balance. The large theropods of the Morrison kept the populations of large herbivores in check, which prevented overgrazing, which maintained the forest composition, which maintained the water quality of the streams, which maintained the conditions in which the whole complicated system continued to function. The sauropods needed the predators in the same obscure way that a fire needs the air that will eventually extinguish it, not consciously, not willingly, but necessarily, because the system only works when all of its parts are present. The Allosaurus finishes drinking. It lifts its head and holds it at medium height, not the full neck extension of alertness, but not the low, relaxed angle of rest. It is scanning the upstream area with the particular quality of attention that a hungry animal gives to a world it is reading for opportunity. The deep amber of the afternoon light catches the texture of its skin, which is not smooth, as older depictions often showed, but finely scaled in the way of a large lizard, with slightly larger scales along the jaw and around the eye sockets that give the face an ancient, armored quality. Some paleontologists have proposed that parts of the skull may have carried keratinous structures, not true crests, but ridges and low prominences that may have added to visual display or even helped in individual recognition. We cannot know for certain. The fossils preserve bone, not the soft tissue that would settle the question. It turns slightly, and for a moment you think it has noticed you. The amber eye sweeps across your direction without pausing, or without appearing to pause, and then continues to the southern fern line. Allosaurus had forward-facing eyes that provided some degree of binocular vision, better depth perception than an animal with eyes set entirely on the sides of its head. But the binocular field was still narrower than that of modern predatory birds, and in the complex visual environment of this forest, with its constant movement of wind-blown fronds and moving insects and the play of dappled light through the canopy, a stationary human-sized figure might register as background rather than as figure. Or the animal has noticed you and has assigned you a category below the threshold of interest. Both possibilities are available. A sound from upstream. Not loud, not dramatic, but specific. The particular quality of a large animal moving through shallow water. A wet impact and splash that is different from the stream's own voice. The Allosaurus head comes up fully now, both eyes forward, the binocular field engaged. The body stills completely. The way a large animal stills when it shifts from one kind of attention to another, when background sensing becomes focus tracking. The tail, which had been swinging slightly in a slow pendulum, goes horizontal and rigid, the counterbalance of the theropod body becoming suddenly active. Whatever is upstream, it has heard the Allosaurus too. The splashing sound stops. The stream returns to its own single voice. There is a long moment of complete stillness, the predator at the stream and the unknown animal upstream both holding the exact position they were in when the other made itself known, both running the same calculation, which is the question of distance and angle and the weight of risk against the weight of opportunity. The Allosaurus moves first, not toward the stream. It turns, quite calmly, and steps back into the fern wall from which it emerged, disappearing into it with the same unhurried deliberateness with which it appeared. The ferns closing behind it, the stillness returning, as though the animal was a momentary detail in a scene that is fundamentally unchanged. The forest settles back into its afternoon patterns. The insects return to their altitudes. The small lizard-like animals reappear in the understory, moving through the low ferns as though no interruption has occurred. The stream continues talking to itself in the voice that is always exactly the same and never quite the same. The afternoon light moves slightly to the west, as afternoon light does, changing the angle at which it enters the canopy without changing the temperature it has already pressed into everything it touches. What had been upstream is not visible. Perhaps it was another Allosaurus, a territorial conflict avoided by the logic that most territorial conflicts between well-matched animals are avoided, without injury, without contact, by the simple, mutual acknowledgement of presence. Perhaps it was a large sauropod, whose size alone made the calculation of risk exceed the calculation of opportunity. Perhaps it was something else entirely, something we have not yet found in the fossil record, or have found but misidentified, or have found and named correctly, but do not yet understand well enough to picture moving through a Jurassic stream in an afternoon in the late Morrison period. The forest does not explain itself. It simply continues, in the way that forests always do, in the unhurried accumulation of moments that eventually becomes geological time. There is a world happening at ground level that the story of the giants tends to obscure. We look at the sauropods and the theropods because they are impossible to look away from. Because size at that scale demands attention, the way very loud sounds demand attention, by overriding everything else in the perceptual field. But the Jurassic ecosystem is not primarily a world of giants. It is, as every ecosystem has always been, primarily a world of small things. Insects and lizards and early mammals and frogs and small reptiles, and the 10,000 species of invertebrate that live in the soil and the wood and the water and the leaf litter, and that do the actual metabolic work of keeping the system alive. The giants are the spectacular surface of it. This is the substance beneath. You lower your attention to the ground level, and the forest floor becomes, suddenly, a world within a world. The needle mat on which you rest is not an inert surface. It is a community. If you could see it in detail, which you cannot without equipment that does not yet exist, you would find that each square centimetre of it contains hundreds of living organisms, mites, springtails, nematodes, fungal hyphae threading between the needles like the finest possible net, bacteria in numbers that exceed the total count of every visible animal in this forest by a factor that renders the comparison meaningless. They are all consuming and being consumed, all participating in the cycle of decomposition that is the forest's real engine, the process by which dead matter becomes living matter, becomes dead matter again in the patient, ancient circle that has been turning since the first cell divided in a warm, shallow sea almost 4 billion years ago. At the surface level, just above the needle mat, the forest floor creatures are more visible if you look for them. A millipede, perhaps 10 centimeters long, its body a dark, gleaming curve of segments, moves across the open ground between two root buttresses with the patient, many-legged locomotion that millipedes have used since before the first land plant existed. Millipedes are among the oldest land animals on Earth, their lineage going back nearly 430 million years, more than twice as long as the dinosaurs. They have not changed very much in that time. They found a working configuration early and stayed with it. Something flickers at the edge of your vision. Low. Fast. Gone behind a root before you can bring it into focus. You hold still and wait, and after a moment it appears again at a gap between two fern stems, a small lizard-like animal, perhaps 15 centimeters long, its body slender and built for speed, its scales gleaming dull gold in the amber afternoon light. It is not a lizard, exactly, not yet, but it belongs to the lineage that will produce the lizards and the snakes, and eventually the monitor lizards and the Komodo dragons and all the squamates of the world you know. Here it occupies the precise ecological niche that a house lizard occupies in a hot climate, darting between cover to cover, finding insects, always at the edge of visibility, always operating on the assumption that the world contains things that want to eat it. It is correct in this assumption. The forest floor is a dangerous environment for a 15-centimeter animal. The Allosaurus would not bother, but there are medium-sized theropods in this ecosystem, the Ornitholestes and the Coelurus, and their relatives, animals of roughly turkey or dog size, lightly built, fast-moving, with grasping hands and sharp eyes and the kind of omnivorous opportunism that makes small forest animals a dietary staple. The small lizard thing has evolved every countermeasure available to it. Speed, cryptic coloring, the ability to drop its tail if seized there, a preference for cover over open ground, a pattern of movement that is brief and explosive rather than sustained and visible. It is still alive. It has always been almost not alive. This is the condition of small animals in this forest, and in every forest, permanent proximity to the edge of existence, managed by constant alertness. Now, here is the quietly astonishing part of the ground-level story. Here is the fact that reshapes everything else when it settles into place. Under a root near you, in a small burrow dug into the moist soil at the base of a large conifer, there is a mammal, not a large mammal, a small one, perhaps the size of a modern shrew, with a pointed snout and large eyes and a coat of fine fur that would feel, if you could touch it, remarkably like the fur of a small modern rodent. It is not a rodent. Rodents will not exist for another 100 million years. This is something earlier, something in the long lineage between the cynodont reptiles that preceded mammals and the true mammals that this animal is very close to becoming, so close that calling it a mammal is almost but not quite accurate, depending on which definition you use and which expert you consult. It is nocturnal, most likely. The large eyes suggest adaptation to low light. It is sheltering through the day in the burrow under the root, emerging at dusk to feed on insects and perhaps plant material and whatever else the night offers that is within its capability to eat and outside the capability of the nighttime predators to notice. Its heart, beating very fast, is keeping it at a warm, stable body temperature, regardless of the ambient air temperature, a trick of physiology called endothermy that the cynodont ancestors began experimenting with millions of years before this morning, and that this animal has refined into something close to what you would recognize as warm-bloodedness. The fur insulates. The high metabolic rate generates heat. The compact burrowing body plan minimizes heat loss. All of these features, that seem like they might simply be advantages, are actually survival mechanisms for a small animal living in a world of large, fast reptiles that can operate at temperatures and hours when a cold-blooded animal cannot. The mammals of the Jurassic have found a niche in the hours and the temperatures that the reptiles do not fully occupy. They live in the night and the early morning. They live in the burrow and the root and the dense understory where a large head on a long neck cannot easily follow. They live on the margins, and the margins are theirs completely. One member of this Jurassic mammal fauna was not small. Repenomamus, a mammal from the early Cretaceous but descended from Jurassic lineages, grew large enough to predate small dinosaurs. Fossil evidence of a Repenomamus found with the remains of a juvenile dinosaur in its stomach provides an image that the usual narrative of Jurassic life does not accommodate. A mammal eating a dinosaur. It was, by all accounts, a relatively uncommon event, but it happened. The margins were not always safe for the small dinosaurs either. The small mammal under the root shifts slightly in its sleep. Something in the soil near the burrow has triggered a brief awareness, and the large eyes open for a moment in the darkness of the burrow, reflecting nothing because there is nothing to reflect. And then close again. The heart slows marginally. The breathing deepens. The Jurassic afternoon passes above the burrow, and the small animal in it is unchanged by it, sleeping through the time of the big animals with a patience that has been 30 million years in the making. Around the base of the conifers, in the zone between the root buttresses where the needle mat is thickest and the light is most filtered, there are slugs, large ones, by the standard of modern slugs. Their bodies glistening with the mucus that keeps them from desiccating in air, and that also serves as the medium through which they sense the chemical signatures of their food. They move with the exquisite slowness that is their defining characteristic, each contraction of the muscular foot moving the body forward by a millimeter or two, the antennae extended and reading the environment in a language of smell and touch that has nothing in common with the visual dominant world of the larger animals. The slugs are feeding on the decomposing needle mat, on the fungal hyphae that thread through it, on the microscopic animals that live in the film of moisture between the needles. They are not impressive in the way that the sauropods are impressive, but they are doing essential work. Everything that dies in this forest, every fallen needle and rotting cone and dead insect and shed lizard skin, must be processed back into nutrients that the roots of the living trees can absorb. The slugs and the millipedes and the beetles and the bacteria and the fungal networks are the processing system. Without them, the forest floor would accumulate organic matter faster than it could decompose, and the nutrients locked inside that matter would remain unavailable to the living trees above, and eventually the forest would begin to die from the bottom up, strangled by its own undigested past. This is a conversation that the forest has with itself, below the level of any individual organism's awareness, below the level of the giants who browse the canopy and the predators who hunt in the fern shadow. The ground-level world is the forest's memory, the place where everything that was becomes the material for everything that will be. The afternoon is beginning to cool. Not dramatically, not in the way of a northern autumn afternoon that drops temperature visibly with the sun's angle. This is a warm Jurassic afternoon in an equatorial zone, and cooling is relative here, a change of 2 or 3 degrees that is still well above the temperature at which any of these ground-level animals feel anything like cold. But the change is enough. The insects that spend the heat of the day at lower elevations begin to rise back through the understory. The small lizard thing that had been motionless under a fern frond begins to move again, cautiously, checking angles before committing to any open ground. The mammal under the root does not wake. It is not time yet. Its internal clock, tuned by millions of years of nocturnal evolution to the timing of dusk, knows that the light is still too strong, that the predators most dangerous to it are still active. It sleeps through the transition from full afternoon to late afternoon with the unconcerned thoroughness of something that has learned to wait for its moment. The ground vibration from the north is absent now. The large sauropod has moved out of range, or has settled somewhere to rest through the heat of the day, as large animals in warm climates often do. The insect chorus, which rose and fell and rose again through the afternoon, is settling toward a more steady, less frenetic register, as the light begins its long evening decline. The world at knee height. The world below the knee, it hums and clicks and decomposes and sleeps and watches and moves and holds itself very still, 10,000 kinds of alive in every square meter, doing the actual work of the Jurassic, which is not roaring and running but composting and converting and keeping the whole enormous system operational for millions of years at a stretch. Under the root, the mammal breathes. The fur rises and falls. The small heart keeps its warm, fast time. If you were to travel east from the Morrison forest, following the floodplain rivers as they widen and slow and become richer in sediment, you would eventually arrive at a shoreline, not the Pacific shoreline that occupies the western edge of the modern continent whose bones lie beneath you, but an inland sea, an enormous body of water that occupies the middle of the continent, the way a lake occupies a valley, except that this lake is the size of a small ocean and is connected to true ocean on both its northern and southern ends. Geologists, when they eventually find and study the sedimentary record of this body of water, will call it the Sundance Sea. The Sundance Sea covers an area that in a distant future will include most of Wyoming and South Dakota and parts of Montana and Idaho and Colorado, land that will one day be considered the interior of a continent so thoroughly that the idea of ocean there will seem faintly absurd. But the continent is still forming. The interior of the landmass that will become North America has not yet fully risen above sea level in all its parts. And in this time, in this morning, the sea reaches inland with a quiet, warm permanence that has already lasted millions of years and will last millions more. The shore is not a dramatic shore. There are no cliffs, no crashing waves, no rocky headlands. This is a gentle coast, a long slope of fine-grained sand and silt that grades almost imperceptibly from the solid ground of the floodplain into the shallows of the sea, so gradually that you could walk a kilometer into the water before it reached your waist. The water here is warm, warmer than any tropical ocean you might know, warmer than the Gulf of Mexico in August. Warm in the way that a bathtub is warm, in the way of water that has been sitting under a bright sun in a warm climate for a very long time and has absorbed as much heat as it can comfortably hold. The color of it, in the late afternoon light, is extraordinary. Not the deep blue of cold deep ocean water, but a pale greenish turquoise. The color of shallow warm water over a pale sandy bottom, intensely lit and slightly hazy with the suspended particles that the rivers have been carrying out of the Morrison Highlands for millions of years. The horizon, where the water meets the sky, is a thin, sharp line. Beyond it, the Sundance Sea extends northward to a connection with an Arctic seaway that itself connects to the Panthalassic Ocean that surrounds the breaking fragments of the old supercontinent. But from this shore, the horizon is simply a line where the turquoise becomes the pale grey blue of the sky. Here is what you cannot see from this shore that the geological record will eventually reveal. The Sundance Sea was warm enough, shallow enough, and clear enough in its earliest phases to support reef-building communities. Not the coral reefs of the Cretaceous or the reefs you might know from modern tropical seas, but communities built by different organisms, rudest bivalves and sponges and algae, communities that created complex three-dimensional structures in the shallows, the way all reef-building communities do, by the patient accumulation of calcium carbonate structures over centuries and millennia. The fossils of these communities are found today in the Sundance Formation rocks of Wyoming, preserved in the beige and grey limestone that records the sea floor of this afternoon. Paris, France, in the same world and the same era, was itself underwater, beneath a different shallow warm sea whose limestone records are the reason the city's classic buildings are built from a pale yellow stone that looks like nowhere else. The Jurassic world was a water world in ways the modern world is not. At the shoreline itself, where the warm water moves in and out in the slow rhythm of tides that are slightly stronger than modern tides because the moon is marginally closer and the world is slightly faster in its rotation, there is a rich community of life. Horseshoe crabs, or rather the horseshoe crab ancestors that are not meaningfully different from modern horseshoe crabs, because horseshoe crabs are another of those success stories that evolution reached early and left alone, move in slow processions through the shallows. They are ancient animals even by the standards of this ancient morning. Their design unchanged in hundreds of millions of years. Their blue, copper-based blood already carrying the specialized properties that will eventually make them invaluable to human medicine, which is not a thing that will exist for another 150 million years. Ammonites. The ammonites of the Sundance Sea deserve more than a sentence. These are cephalopods, relatives of the modern nautilus and the octopus and the squid. But they have taken the spiral shell route, and they have taken it to extraordinary lengths. Some species of Jurassic ammonite grow to diameters approaching 2 meters. 2 meters. A shell the diameter of a full-sized car tire, but taller, spiral and ridged and coloured in the pale iridescent way of nacre, the same mother-of-pearl material that lines the shells and gives them, when the light catches them at the right angle, in the right depth of water, a shimmer that has no real analogue in the living world you know. The ammonites move through the water by jet propulsion, drawing water into the mantle cavity and expelling it in pulses that move the animal backward through the sea. The direction of travel, for a cephalopod, is always technically backward. This has never been a problem. Watching an ammonite move through shallow water is a study in ancient patience. The animal does not hurry. It does not need to hurry. The shell, which is an extraordinary structure, is divided internally into sealed gas-filled chambers that the animal regulates to control its buoyancy, filling them with fluid to sink, withdrawing the fluid to rise, managing its position in the water column with a precision that requires no thought, operating instead by the same osmotic physiology that the ancestors of the nautilus have been using since before the first fish appeared in the sea. The animal lives in the last and largest chamber of the spiral shell, the opening of which faces forward in the direction of travel. The tentacles extend from this opening, feeling the water for food, for chemical signals, for the specific signatures of prey and predator that the ammonite's world is written in. The water here at the shore is also full of belemnites, squid-like animals that lack the external shell of the ammonites and instead carry an internal structure, a cigar-shaped guard of solid calcite that fossilizes well and is found in enormous numbers in Jurassic marine deposits. The cigar-shaped guards so abundant in some formations that geologists call them bullet stones and pick them up by the handful. The living belemnites are fast and schooling, moving through the Sundance shallows in silver-flashing shoals that change direction with the kind of instantaneous collective precision that schooling fish display, a property that emerges from simple rules followed simultaneously by every individual, not from any central coordination, not from any leader. The school is the behavior, and the behavior produces something that looks like intention without requiring it. Wading birds would eat the belemnites if wading birds existed. But wading birds, like all birds in the form you know them, are still in the future, still latent in the theropod lineage, still waiting for the particular set of circumstances that will tip feathered non-avian dinosaurs into the fully committed aerial lifestyle that will eventually define the class Aves. What hunts the belemnites here are the fish, which are various and numerous and not well known to most people because the fish of the Jurassic seas rarely make the lists of impressive prehistoric animals, overshadowed always by the marine reptiles. The fish deserve better. The Jurassic seas were full of them, some familiar seeming, some profoundly strange. Ray-finned fish not dramatically different from modern bony fish moving in schools through the shallows. Sharks that are the ancestors of modern sharks but smaller and more varied in form than the apex shark of public imagination. Beyond the shallows, in the deeper water that the shore grades into without any dramatic transition, the sea changes character. The turquoise of the shallows deepens to a blue-green, then to a blue that gradually loses its green component as the depth increases and the light penetrates less. In this deeper water, the ammonites are larger, the belemnite schools are denser, and the marine reptiles, which are the true lords of the Jurassic oceans, cruise through the middle water and the surface with a sovereignty that the great theropods exercise over the land. You can see one from the shore, just barely. A dark shape moving below the surface, about 200 meters out. Visible as a shadow rather than a form, its outline indistinct through the haze of suspended particles. It is long. It is moving with purpose, not the patrol-level movement of an animal searching for food, but the directed movement of an animal going somewhere specific, following a current perhaps, or a temperature gradient, or the chemical trail of a prey school that it detected an hour ago and has been tracking since. The shadow fades into the haze of depth and distance and is gone. The shore itself is warm under the afternoon sun. The sand here, where the tide is currently withdrawing, is wet and dark and densely textured with the tracks and trails of the animals that live in and on it. The horseshoe crab furrows, the paired marks of bivalves that have been working their way into the substrate, the surface trails of worms and small crustaceans. The whole intertidal zone is a written record of the morning's activity, which the next high tide will erase and which the organisms will then spend the following low tide rewriting. The smell at the shore is sharp and alive in a way that inland forest smells are not. Salt and iodine and the particular organic richness of warm, shallow water at low tide, where the retreating sea has left strands of algae and the small animals that were sheltering under them. It is not an unpleasant smell. It is one of the oldest smells available to any creature that has ever lived on the edge of the land and the sea. A smell that triggers something in animal nervous systems that goes back much further than any conscious response. Something that says, water is here, food is here, this is a place worth being. The sun is lower now, and the turquoise of the Sundance Sea has taken on the copper and rose of early evening. The ammonites are moving into deeper water, following the light change that tells them, through the photoreceptors in their eyes, that the transition time between day and night is arriving. The belemnite schools have dispersed into individual feeding mode, single animals moving through the water column in quick, precise darts that are nothing like the collective shimmer of the daytime school. A breeze comes off the water, cooler than the afternoon air, carrying the smell of the open sea. You feel it against your face and your forearms. It has come a long distance, this breeze, all the way from the northern connection of the Sundance Sea with the great circumpolar ocean that surrounds the high latitudes, and it carries in its smell the faintest trace of something colder and wilder than anything in this warm, shallow, gentle shore. The ancient sea turns copper in the evening light, and the shadow in the deep water, that might have been a marine reptile does not return, and the horseshoe crabs continue their slow procession in the shallows with the unhurried certainty of things that have been doing this since before the concept of urgency existed. The world at the edge of the land and the water is always a threshold place, always a place where categories dissolve into each other. The Jurassic shore is no exception. Here the land becomes the sea, gradually, without drama, and the sea becomes the land in the same slow way. Between them, in the zone of both and neither, the ancient life of the Sundance settles into evening. The shadow you saw from the shore had been an ichthyosaur. The word ichthyosaur means fish lizard, which is not the most accurate description of an animal that is neither fish nor lizard, but a fully fledged marine reptile whose ancestors walked on land, whose descendants will include some of the most sophisticated marine hunters in Earth's history, and whose convergent evolution toward the dolphin body plan is one of the most frequently cited examples of the principle that similar environments produce similar solutions, regardless of what lineage the solution starts from. The ichthyosaur looks like a dolphin the way that a dolphin looks like a fish. The resemblance is real and instructive and tells you something important about the physics of moving efficiently through water, but the similarity is surface level in the precise sense. Below the surface, the biology is entirely different. The ichthyosaur, moving through the deeper water of the Sundance Sea, is about 4 meters long, a mid-sized adult of one of the many species of ichthyosaur that populate the Jurassic oceans. Its body is streamlined, tapering from a broad midsection to a narrow caudal fin that drives the animal forward with vertical strokes, the way a fishtail drives a fish. This is different from a dolphin, whose tail moves horizontally, a mammalian adaptation reflecting terrestrial ancestors that ran on 4 legs. The ichthyosaur tail moves vertically because the ichthyosaur's terrestrial ancestors moved like reptiles, with a horizontal body motion, and the transition to aquatic life was complete enough to produce a fish shape, but not complete enough to reorient the tail stroke that evolution had been refining since the first land animal's ancestors. The eyes of the ichthyosaur are extraordinary. In several species, the orbit, the bony eye socket, is the largest relative to body size of any vertebrate known in the fossil record, in some individuals exceeding 30 centimeters in diameter. Eyes that large gather an enormous amount of light, which means they are adapted to seeing in conditions of very low light, which means their owners were diving deep, to depths where sunlight barely penetrates, to hunt prey that lives in near darkness. Here is a fact worth holding for a moment. Certain ichthyosaurs had eyes larger than those of any other vertebrate that has ever lived, larger than the eyes of the blue whale, larger than the eyes of the giant squid. What they saw in the deep water below the Sundance Sea is something we can only approach from the outside. We know the physics of the eye. We know the depth at which light of various wavelengths becomes unavailable. We can extrapolate the kind of world those eyes were reading, but the experience of it is gone. The ichthyosaur swims at a depth of about 20 meters, in water that is warm at this depth, warmer than any equivalent depth in the modern ocean, because the Jurassic world has no thermocline to speak of in the inland seas, no cold water upwelling from the deep to stratify the water column. The temperature from surface to floor is nearly uniform. This means the oxygen content of the water is also more uniform than in modern seas, which means the chemical landscape that the ichthyosaur navigates through smell and water pressure detection is also more uniformly distributed, which means prey can be anywhere, not concentrated at the depth boundary between warm surface water and cold deep water the way it is in modern oceans. The ichthyosaur hunts by sight and by a lateral line system, a row of sensory cells along the sides of its body that detect pressure changes in the water, the same kind of system that fish use to navigate in murky water and to feel the movements of schooling companions. In very clear water, like the Sundance Sea, the visual system probably dominates. The ichthyosaur's enormous eyes, adapted for dim light, must be somewhat dazzled in the clear surface water of the afternoon, the way a human eye designed for low light is dazzled in bright sun. The animal keeps to the middle water, where the light is adequate but not overwhelming, where the hunting conditions match the design of its sensorium. Here is something about ichthyosaurs that was confirmed only when a particularly well-preserved fossil was discovered with embryos inside the body cavity. Ichthyosaurs gave birth to live young, not egg-laying as you might expect of a reptile, but live birth. the young born tail first into the water just as modern dolphins and whales are born, to prevent drowning before the lungs are fully functional. The fossil record shows this not only in specimens with embryos inside them, but in at least one spectacular specimen where the birth appears to have been preserved in progress. The young animal partially emerged from the mother at the moment of death. These animals, returning to the sea from land-living ancestors, independently re-evolved live birth, independently re-evolved many aspects of the dolphin physiology, independently arrived at the conclusion that a streamlined, tail-propelled, warm-water body plan was the correct answer to the question of how to live successfully in the Jurassic Sea. The sea itself is asking a different question in the deep water below the ichthyosaur's current depth. At the floor of the Sundance Sea, in the accumulated lime mud that the shells of billions of microorganisms have been raining down onto the floor for millions of years, there is a different community, bottom-dwelling bivalves, buried in the mud, with only their siphons extended into the water column, filtering the organic particles that drift down from above. Sea urchins moving slowly across the mud surface, their tube feet finding purchase in the fine silt. Brittle stars, radially symmetrical like their starfish relatives, but with long, flexible arms that move in the rippling, wave-like coordination that the nervous system of an echinoderm produces when it needs to move quickly across the seabed. The floor of the Sundance Sea is a world of extraordinary quiet, not absolute quiet. Water transmits sound more efficiently than air, and there is always sound in the ocean. The creak and crack of sediment settling, the distant percussion of waves on the shore, the sound signatures of the swimming animals above. But it is a muffled world, a world where the visual component is reduced to the ambient dim light that reaches 20 or 30 meters of water depth, where chemical communication and pressure sensitivity replace the visual dominance of the shallower zones. Animals here move with a slowness appropriate to their sensory environment. There is no point in speed when the world you are navigating is too dark to see more than a meter ahead. The ichthyosaur does not descend to the floor. It hunts in the middle water, where the light is still adequate, where the schools of belemnites and fish that are its preferred prey are most concentrated. It has been diving and surfacing in a regular pattern since morning, spending perhaps 4 or 5 minutes at depth before rising to the surface to breathe, a respiratory rhythm enforced by the physiology it inherited from its land-living ancestors and never fully transcended. The Jurassic Sea does not belong to the ichthyosaur in the way the Jurassic land belongs to the sauropods. The sea is an environment the ichthyosaur has learned to exploit brilliantly, but must periodically leave, must rise through the water column into the alien domain of air, must breathe the air briefly and return. It has made this compromise for 50 million years, and it has worked, and the ichthyosaurs are numerous and successful, and will remain so until changes in ocean circulation and food web structure in a different and more distant future make conditions difficult for them. At the surface now, the ichthyosaur rises. The head breaks water, a narrow pointed snout followed immediately by the smooth top of the head with its single nostril, which opens and exhales the used air in a small spray. The breath is quick, the nostril closes, the head submerges. The dorsal fin, a tall curved structure, not unlike a dolphin's dorsal fin but proportioned differently, cuts the surface for a moment. Then the animal is gone. Down into the water, with the unhurried efficiency of something that has made this motion millions of times. There are other large animals in this sea, the plesiosaurs, long-necked marine reptiles that are in some ways the ichthyosaur's counterpart, and in some ways its complete opposite. Where the ichthyosaur is streamlined and fast and built for pursuit, the plesiosaur is broad and slow and built for patience, its 4 paddle-like flippers moving through the water with the same motion that penguins use, flying through water rather than swimming it. The neck of a long-necked plesiosaur, extended to its full length, is almost half the animal's total body length, a neck proportionally similar to the sauropods of the land but evolved independently and to a different purpose, not for reaching the upper canopy of conifers but for a kind of ambush hunting in which the long neck allows the body to remain at a distance while the head is brought close to a school of fish without disturbing it until the last moment. Here is another piece of convergent evolution worth noticing. The ichthyosaur swims like a fish, the plesiosaur swims like a bird. Both are reptiles, both are in the Jurassic Sea. Both evolved their locomotion independently from 4-limbed land ancestors. and they arrived at two completely different solutions to the same problem, solutions so divergent in their principles that they could serve as the two canonical answers to the question of how to move through water. As the sun descends further and the copper evening light penetrates the water at a lower angle, the surface of the Sundance Sea becomes a plane of rose and bronze, and the ichthyosaur's back fin cuts through this plane at intervals as the animal continues its surface-to-depth cycle, a rhythm as regular as breathing because, fundamentally, it is breathing. Elsewhere on the surface, in the far middle distance, something larger disturbs the water, a longer, heavier displacement, a plesiosaur perhaps, surfacing more slowly and sinking back more deliberately, the large flippers providing momentum that carries the animal several meters horizontally with each stroke. The evening transition in the Jurassic Sea is a movement of organisms toward the surface. Many animals that have been at depth through the day follow the light upward as it retreats toward the surface layers. The shrimp-like creatures called euphausiids, the ancient ancestors of modern krill, ascend through hundreds of meters of water in the daily vertical migration that is one of the largest coordinated animal movements on Earth. The fish that feed on them follow. The ichthyosaurs, detecting the concentration of prey near the surface, feed heavily in these twilight hours. The water is warm, the evening is long and copper-colored. The Sundance Sea, which covers a third of a continent, breathes in the slow rhythm of an inland sea that has been here for millions of years and is in no hurry to be anywhere else. And in the deep water below everything, in the lime mud that records each day as a thin layer and each century as something you could measure with a ruler, the bodies of the organisms that died today are settling slowly toward the floor, becoming part of the record, becoming the limestone that a different world will eventually quarry for its buildings and study for the stories compressed inside it. The ichthyosaur surfaces one more time, breathes, and descends into the darkening water. The sea closes over it like a thought. If you have already found the edge of sleep, let yourself cross it. Subscribe so there is always another ancient world waiting for you. Sleep well. The evening sky above the Morrison Forest has gone the color of pale ash over the eastern horizon, darkest there where the sun has fully left, and still holding a faint trace of warmth to the west where the day is not quite finished. In between, the sky is that particular Jurassic shade of deep blue-gray that has no analogue in any modern sky because the Jurassic atmosphere has a slightly different composition, slightly more carbon dioxide, slightly different aerosol content, a sky that scatters light in proportions that produce colors the human visual system would recognize but would struggle to name. Against this sky, in the last light, things are flying. They are not birds. The lineage that will produce birds is still on the ground, still feathered but not fully committed to the air, still, in the gradual process of discovering what feathers can do when enough of them are arranged in the right way on a limb shaped by millions of years of selection toward a particular purpose. What flies in the Jurassic sky is something that will not be in any modern sky, something that will not survive into the world where birds inherit the air. These are pterosaurs, the flying reptiles, and they are extraordinary animals. Extraordinary for the specificity of their design, for the fact that they discovered vertebrate flight independently of and millions of years before the birds. The wing of a pterosaur is built around a single enormously elongated fourth finger, not the whole hand. As in a bat, where the wing membrane stretches between all four elongated fingers. Just one finger, the fourth, stretched to a length that in a large species exceeds the entire length of the rest of the body, with the wing membrane, called the patagium, stretching from the tip of this one finger all the way to the ankle of the hind leg. This is a different solution to the problem of flight than anything else that has ever tried to fly. The pterosaur finger is the primary structural element of the wing, and it must be both enormously strong to withstand the forces of flight and surprisingly light to avoid adding mass that the wing would then have to lift. Here is the fact about pterosaur weight that is genuinely difficult to believe until you understand the engineering. A Rhamphorhynchus, a common Jurassic pterosaur with a wingspan of roughly 90 centimeters to 1 meter, weighed somewhere in the neighborhood of 150 grams, less than half a pound, a wingspan of a meter, and the weight of a large apple. The bones are hollow to an extraordinary degree. The walls reduced to paper-thin tubes of bone surrounding an airspace, the skeleton a marvel of structural engineering that achieves maximum rigidity from minimum material mass. The Rhamphorhynchus flying overhead this evening is lighter than any bird of comparable wingspan that will ever exist, lighter than many of the insects it shares the air with. There are several of them visible, moving in and out of the shadow line, where the forest canopy meets the open sky above the floodplain. They move differently from birds, which is one of the ways you know, watching them, that you are somewhere very old. The wing beat is slower in proportion to body size, more deliberate, each stroke covering more air. The long tail of Rhamphorhynchus, with its distinctive diamond-shaped tail vein, works as a rudder and stabilizer. The head is carried slightly forward and down, the long, tooth-bearing beak extended, ready. The eyes are large and positioned for binocular forward vision, the forward-facing eyes of a pursuit predator. They hunt by sight. In the last light, which for most animals in the forest is the signal to seek shelter, the pterosaurs are finding the upwelling columns of warm air that form along the edge of the forest, as the air over the open floodplain cools faster than the air over the canopy. These thermals are weakening now but still present, and the pterosaurs exploit them to gain altitude with minimal energy expenditure, spiraling up on outstretched wings in the way of eagles and vultures and large gliding birds, though the pterosaurs are doing this not to gain height for a long glide, but to get above the evening insect clouds that form over the floodplain when the temperature reaches the particular threshold that triggers emergence. The insects come up from the floodplain in columns of remarkable density. They are primarily small, the flying adults of species whose larvae spent the day in the mud of the shallow pools that the recent monsoon has left scattered across the floodplain surface. They fly upward, not because they intend to fly upward, not with any navigational purpose that we would recognize as navigation, but because they evolved in a world where upward movement was the correct initial response to the cue of open sky above still water, a response that eventually connected them to others of their species in the air, and led to the mating flights that are what all this emergence is actually for. They do not know they are food. They are simply following the imperatives of their design. The Rhamphorhynchus know they are food. The pterosaur swings toward a dense cloud of emerging insects with its beak slightly open, banking with a precision that the asymmetric loading of a bat's wing would not achieve, the long stabilizing tail working to keep the turn flat and controlled. It passes through the insect cloud, and its beak snaps closed on several insects simultaneously. Not the quick, precise strike of a flycatcher, but a sweeping, gathering motion, the teeth an array for retention rather than a tool for precision. It swallows while banking back into position. It passes through the cloud again. There is another pterosaur in the Jurassic sky tonight that you do not see from the forest edge because it has already gone to roost on the far cliff face of the canyon to the southeast, but whose existence here is worth knowing. Dimorphodon, a shorter-winged, larger-billed pterosaur, is something of a mystery. Its beak is disproportionately large relative to its body, giving it a somewhat puffin-like profile. And the theories about what that beak was for, what selective pressures produced it, remain unsettled. Dimorphodon may have been a fish-eater at the water's edge. It may have been a generalist, taking insects, small vertebrates, fish opportunistically. It may have been something we have not imagined. The fossils preserve the structure, but not the habit. And the habit is what we most want to know. The pterosaurs are not the only things in the air this evening. Something slower, lower, and much smaller moves through the dimming air between the canopy and the first cliff face. It moves in the erratic, unpredictable course of an animal that is hunting small moving things in 3 dimensions, making rapid directional changes that seem random from outside, but are actually the specific responses of a visual system tracking individual insects through visual fields that overlap in complex ways. This is a small feathered theropod, a microraptor relative perhaps, using the transition hour between day and night to catch insects that neither the daytime reptiles nor the truly nocturnal hunters have claimed. It is not a bird, but it is as close to a bird as anything alive on this evening has managed to become. The pterosaur world is a world of silence in a specific sense. These animals did not produce the constant vocalizations that modern birds produce. Evidence for pterosaur vocalization is essentially absent from the fossil record. The throat structures that allow birds to sing did not exist in pterosaurs. They may have produced hisses, low calls, perhaps sounds for close-range communication during courtship or territorial disputes, but the sky above the Jurassic floodplain at dusk did not ring with the calls of the flying things, the way a modern forest edge rings at dusk with the sounds of birds going to roost. It was a quieter sky, animated with the movement of wings, but not with the complexity of the avian voice. The light is almost gone now. The western horizon holds a last band of warm color, deep rose at the base and fading through orange to the pale sky above. And against this band, the pterosaurs are visible as silhouettes, the wingtips sharply defined against the light, the long tails of the Rhamphorhynchus, adding a distinctive trailing element to the silhouette. They are folding their wings now, gradually, finding their way toward the roost sites they return to each evening, the cliff faces, and the large horizontal branches, and the sheltered overhangs where they will hang through the night. How pterosaurs roosted is not entirely settled. Some researchers have proposed that they hung from their feet like bats. Others have proposed that they roosted more like birds, perched on horizontal branches or flat surfaces, wings folded. The wings fold in a specific way, along the elongated fourth finger and against the body, reducing the span to a small fraction of its flight configuration, allowing the animal to fit into spaces that the opened wing would prohibit. A roosting pterosaur, wings folded, would be an animal of modest size, unremarkable in appearance until it opened its wings and became something that redefined the visual space it occupied. The last Rhamphorhynchus vanishes into the shadow of the cliff face. The evening sky above the Morrison forest completes its transition from the day colors to the night colors, the deep blue darkening toward black at the zenith, the first stars appearing in the east over the distant Sundance Sea. The air above the forest is empty of large, visible things for the first time since dawn. The insects continue, lower now, closer to the ground, following the warmth as it retreats downward from the sky through the canopy and into the still warm surface of the forest floor. Something small and quick moves through the low ferns, hunting them. It does not fly, not yet, but it has feathers, and it has the beginning of what flight will eventually become. And it is in no hurry, because evolution is never in a hurry. And what flight requires of the body is still being worked out, generation by patient generation, in the dark between the ferns. The valley opens up below the forest, wide and shallow, its floor a mosaic of different textures. In the wetter areas near the river that threads through its center, the ground is soft and dark and covered with the horsetails and water ferns that grow wherever water is reliably present. On the slightly higher ground to either side, the cycads are dense, their thick trunks in regular spacing as though planted by design, their crowns spreading above head height in dark, feathery fans. At the margins of the valley, where the ground begins to rise toward the forest, the conifers take over, their shadows extending into the valley in long evening bars. In the valley, there are Stegosaurus. There are 4 of them visible from the ridge where you stand looking down. A large adult, perhaps 9 meters from the pointed snout to the end of the tail, 2 mid-sized animals that are probably young adults, and 1 smaller individual that may be a juvenile of 2 or 3 years. They are spread across the valley floor in loose proximity, not in a tight herd but not in solitary isolation either, maintaining the kind of spacing that suggests mutual awareness without social dependency. Each animal is engaged in the activity that Stegosaurus apparently spent most of its time engaged in, which is eating. The low-slung head works through the cycad understory, the beak-like front of the snout clipping vegetation at ground level, and passing it back to the cheek teeth for processing. The plates. The bony plates of the Stegosaurus are the feature that has generated more scientific debate than any other aspect of the animal, and they deserve attention. They run in 2 rows down the back of the animal, not in a single interlocking row but in 2 offset rows that alternate from side to side, creating the distinctive double-sail appearance of the most famous living reconstruction. The plates are large, the largest ones over the hips, reaching perhaps a meter in height. They are made of a material called ossified cartilage, not the dense, compact bone of the skull and limb bones, but a more porous, vascularized material. This porosity, the presence of many small channels through the plates, is significant. The debate about the plates centers on their function. They may have been for thermoregulation, the high surface area, and rich blood supply, allowing the animal to absorb heat quickly in the morning sun, or to radiate excess heat in the afternoon, pumping blood through the plate network to modify its temperature. They may have been for display, the visual signal of large plates, and possibly the ability to flush them with blood, in ways that changed their apparent color, a signal of health and genetic quality to potential mates, or a threat signal to potential rivals. They may have been some combination of both. They were certainly not primarily defensive, which seems counterintuitive given that they look like armor. The plates of Stegosaurus would deflect little of the force of an Allosaurus bite. They are positioned along the back in a way that suggests display more than protection. The real defensive weapons of the Stegosaurus are at the other end. The thagomizer. The tail spikes of Stegosaurus were named, informally, by a paleontologist who could not resist acknowledging a Far Side cartoon that depicted them by that name. The thagomizer. It is now the preferred informal term, adopted into the scientific literature with the kind of affectionate reluctance that science sometimes reserves for names that are too good to ignore. The thagomizer consists of 2 to 4 pairs of spikes at the tail tip, made of solid bone unlike the plates, each one a long, tapering, laterally flattened structure that in a large adult could reach a meter in length. Healed bite marks in Allosaurus bones and puncture wounds in Allosaurus vertebrae that match the diameter of Stegosaurus spikes provide evidence that this tail was used actively and effectively. The large adult Stegosaurus in the valley swings its tail as you watch, a slow, horizontal sweep that is not particularly dramatic, but is a reminder that the tail is always available, always in motion, its considerable leverage making the tips of the spikes move through arcs of considerable speed when the tail is swung with intention. The tail itself does not feel threatening in this context, in the dusk light of the valley, with the animal absorbed in feeding. It is simply part of the animal, part of the horizon of the body. Something the animal has been swinging in the same slow rhythm since it was old enough to swing it. Here is the fact about the Stegosaurus brain that gets repeated in almost every account of the animal, not because it is the most important thing about the Stegosaurus, but because the mind tends to hold it with a certain wonder that it has trouble releasing. The brain of a large Stegosaurus was approximately the size of a walnut. An adult animal 9 meters long and weighing perhaps 2 to 3 metric tons carried a brain smaller than the brain of many modern birds. This is often cited as evidence of stupidity, but this framing does the animal a disservice. The Stegosaurus survived for millions of years. It was enormously successful. It occupied its ecological niche with a competence that no other animal displaced for tens of millions of years. A walnut-sized brain, it turns out, is entirely adequate for the requirements of a large herbivore whose life consists of eating cycads and defending itself with its tail, and which does both very well. There was, for many years, an additional idea, now largely, but not entirely discarded, that the Stegosaurus had a secondary nerve cluster in the region of its hips, sometimes called a second brain, that helped coordinate the back legs and tail independently of the brain proper. The structure is real. The sacral region of the spinal cord does contain an expanded neural ganglion, but calling it a second brain overstates what it does. Modern crocodilians and birds have similar structures. It is better understood as a local processing center, a way of reducing the reaction time for certain movements that would be unacceptably delayed if every signal had to travel all the way to the head and back before the leg could respond. The tail that swings in the valley this evening is coordinated in part by this sacral ganglion, the Stegosaurus's ancient solution to the problem of having a very long body and a brain at one end of it. The juvenile Stegosaurus has moved toward the river and is drinking from a shallow bend where the water slows and deepens slightly over a bed of fine silt. The drinking posture requires the front legs to splay slightly to bring the small head close to the water surface. The plates are already present on the juvenile, though proportionally smaller relative to body size than those of the adult, and already alternating in their double row along the back. The animal drinks with the same unhurried rhythm with which it does everything else. The Stegosaurus life appears to be a life of minimal urgency. Eat. Drink. Move to the next stand of cycads. Drink again. Rest through the midday heat. Return to eating. Sleep in the open where the large body can radiate heat through the night. The larger of the 2 mid-sized Stegosaurus has moved toward the adult, in what might be a social gesture, or might simply be the movement of an animal following a successful forager to better food. They stand in proximity for a few minutes, both feeding from the same stand of cycads, their plates very close, and occasionally nearly touching. There is no obvious interaction between them, no affiliative behavior that we would recognize as bonding or communication. But neither is there aggression, no displacement behavior, no assertion of dominance. They simply share the space and the food for a while, before the younger animal drifts north toward the denser cycad growth along the river's edge. Here is something about the Morrison Formation ecosystem that the Stegosaurus embodies particularly well. This was a world that had been stable for an extraordinarily long time. The ecosystem of the Morrison is not a snapshot of a moment, but a record of millions of years of relative stability. The same genera appearing in the fossil record layer after layer, slightly changed, but recognizably continuous. The same relationships between predator and prey and browser and landscape maintained across geological intervals. The Stegosaurus in this valley has ancestors who looked almost exactly like it 10 million years ago. Its descendants, if we were to look forward from this evening, will look almost exactly like it for several million years to come. This is not evolutionary stagnation. This is evolutionary success so complete that the question of change does not arise. When a design works this well, time does not improve it. The sun has left the valley floor now, though the ridge behind you still catches the last light. The valley has taken on the blue-grey light of dusk. The colours muted and the edges softened. The Stegosaurus continue to feed, their white plates catching what light remains and giving them a faint phosphorescence in the dimming. This luminous quality of the plates in low light may or may not have been their actual colouring. The pigmentation of the plates, whether they were plain bone white or striped or spotted or flushed with colour, is completely unknown. We have the structure. We have some evidence of vascularization. We do not have the colour. Some researchers have proposed that the blood flushing that the plate's rich vascular supply would allow could have produced visible colour changes, the plates reddening when blood was pumped into the surface vessels, perhaps during threat display or courtship, then returning to a paler colour when the blood retreated. If this is correct, the Stegosaurus in the valley this evening is performing a kind of communication we cannot read, sending signals in a colour language that left no record in the bones. The valley grows darker. The Stegosaurus becomes silhouettes against the lighter surface of the river. Their distinctive profile unmistakable at any light level. The arching back, the high plates, the thagomizer trailing behind. They have moved toward each other as the light fails, not tightly grouped but closer than they were in the afternoon, as though the darkness is a reason for proximity that the daylight hours do not provide. The valley is quiet, in the way of a place where large animals are present, but not moving urgently. The river makes its patient sound. The cycads are still. The insects above the water have formed their column, and the column has begun to thin as the temperature drops, and the insects that are still flying retreat to cover. The Stegosaurus settle. The large adult folds its front legs and lowers its belly to the ground, the plates spreading to either side in the horizontal position they take when the animal reclines. The others follow, in the slightly staggered way of animals that do not move in coordinated groups, but arrive at the same conclusion by the same logic at approximately the same time. The valley floor holds the heat of the day in its silt and clay, and the warmth rises from it in the way that heat always leaves the earth in the evening, slowly, from the top down. The Stegosaurus rest in it. The plates, if they absorb and release heat as some theories propose, are slowly giving back what they gathered through the afternoon. The world is very quiet, and the ancient armoured animals sleep as they have always slept, in the open valley, under the enormous and indifferent Jurassic sky. In the late Jurassic world, in a place that will one day be called Bavaria, in a shallow tropical lagoon that is warm and hypersaline and surrounded by low limestone islands, something dies and sinks to the bottom. The water is so calm and so salty and so depleted of oxygen at the lagoon floor that nothing disturbs the body. As it settles into the fine lime mud, it lies there, and the days pass over it, and the mud slowly and patiently covers it, and the calcium in the bones slowly and patiently replaces itself with the calcium of the surrounding sediment, and what was a living animal becomes, across millions of years, a fossil of extraordinary completeness and detail. This is the Archaeopteryx, and when the fossils are eventually discovered in the limestone quarries of Bavaria in the 1800s and shown to the scientific community, they arrive at a moment when a particular question is very much in the air. The question is whether life has always been as it is, or whether it has changed over time, and if it has changed, how. The Archaeopteryx fossil arrives into this question like an answer that has been waiting in the limestone for 150 million years. It has feathers. It has the feathers of a bird, arranged in the pattern of flight feathers, visible as impressions in the fine limestone that preserved them with a fidelity that bone alone could never have achieved. But it also has teeth and claws on its wings and a long bony tail. The body beneath the feathers is a small theropod dinosaur, unmistakably a member of the Coelurosaur lineage that is converging on flight from the ground up, developing the feathers and the hollowed bones and the reduced size that will eventually produce the birds. Archaeopteryx is the most famous transitional fossil in the history of paleontology, not because it is the only one, or even the most dramatic, but because it appeared at precisely the right moment in the history of science to illustrate the principle of evolutionary transition in a way that bone alone had not previously managed to do. The feathers made it real. The feathers said, "This is what change looks like from the inside." The change is not a leap, not a transformation from one thing to another in a single dramatic step. The change is this: a small dinosaur with feathers that are almost but not quite the feathers of flight. A small dinosaur that can almost but not quite fly in the way that a bird flies. Whether Archaeopteryx could fly at all is still debated, which is a remarkable thing to say about an animal famous primarily as the first bird. The anatomy of the flight muscles is not directly preserved in the fossil record. The bones of the sternum, where the large flight muscles attach in modern birds, were not fully ossified in Archaeopteryx, which may mean the flight muscles were not as large as in a modern bird of similar size, which may mean the animal could not generate the sustained flapping flight of a modern bird. Or it may mean only that we have found specimens at an age where the sternum had not yet fully hardened and that older adults had full flight capability. The question remains open, and it will remain open until we find evidence that the current specimens have not provided. What we know with more confidence is the brain. Studies of the skull cavities of Archaeopteryx fossils have allowed researchers to reconstruct the approximate size and shape of the brain, and what they found was not what you might expect from an animal that is otherwise a small theropod dinosaur. The brain of Archaeopteryx shows enlargement in the regions associated in modern birds with visual processing and the complex coordination required for flight, and reduced regions associated in non-avian dinosaurs with smell. It is, in its brain proportions, more similar to modern birds than to the non-avian dinosaurs it most closely resembles in its skeleton. This suggests that the neural infrastructure for flight, the brain machinery for processing rapid visual information in 3 dimensions and coordinating the complex movements of wings, was in place in Archaeopteryx, whether or not the muscular system was quite ready to use it. Here in the Jurassic world itself, before the fossils, before the limestone, before the quarries and the museums, the Archaeopteryx is simply an animal, a small animal about the size of a modern crow, with dark feathers and a long tail and clawed wings that it uses to climb among the branches of the trees near the lagoon shore. It is probably not a strong flyer in the sense of sustained long-distance flight, but it moves between trees. It launches from a branch, spreads its wings, and crosses a gap of several meters with controlled gliding flight that may include some powered wing beats or may not. It lands with its clawed wings extended, gripping the branch in a posture that looks like neither a bird's landing nor a reptile's, but something precisely between. The feathers are real feathers, not proto-feathers, not the simple filamentous structures that some theropod dinosaurs carry as insulation or display. The primary flight feathers of Archaeopteryx are fully differentiated, with a central rachis and interlocking barbules that give the feather its familiar flat, smooth surface. How the feathers arrived, the evolutionary pathway from simple filament to complex flight feather, is one of the most intensely studied questions in paleontology, and the answer, which has been assembling itself over the past several decades, as new feathered dinosaurs have been found in China and elsewhere, is that the transition was long, stepwise, and involved feathers for many purposes before it involved feathers for flight. Feathers for insulation came first, then feathers for display, then feathers for brooding eggs. The evolution of flight feathers may have happened in 2 directions simultaneously. From the trees down, in animals that used feathered limbs to improve gliding between trees, and from the ground up, in animals that used feathered forelimbs to improve running performance on rough terrain. The Jurassic ecosystem contains both kinds of animals. The Archaeopteryx near the lagoon is the descendant of whichever pathway worked, or of both. Here is a quiet fact. The feathered theropods of the Jurassic and early Cretaceous were not a minor sideshow to the main event of the dinosaur world. They were numerous and varied, and ecologically significant. Microraptor had 4 wings, feathered forelimbs and feathered hind limbs, and could glide and possibly fly from trees. Epidexipteryx had elongated display feathers on its tail. Sinosauropteryx had a coat of simple, filamentous protofeathers over its entire body. The sky and the canopy and the understory of the late Mesozoic were full of things with feathers that were not birds, doing different things with those feathers than birds eventually did, exploring the evolutionary space around flight before flight was fully defined. The Archaeopteryx near the lagoon perches in a low tree at the water's edge, its long tail hanging below the branch, its clawed wings folded. It is watching the water. The lagoon in the evening light is a mirror, reflecting the pale sky with a precision that still water always achieves, a precision that seems to double the world, to offer a second version of it below the first. The Archaeopteryx sees movement below the surface. Something small, a fish perhaps, disturbed by the evening thermal changes and coming briefly toward the surface. The animal on the branch shifts its weight, its head tilting in the precise, alert way of a creature that is assessing an opportunity. It does not dive. Whatever the opportunity was, it passes. The surface of the lagoon resettles. The Archaeopteryx returns to its previous posture, the head settling slightly, the attention released from sharp focus to the broader, softer monitoring of an animal that is not currently doing anything specific, but is ready to do something, if something presents itself. The biology of Archaeopteryx tells us that the boundary between non-avian dinosaur and bird was not a line but a gradient, a transition so gradual that drawing a line across it has more to do with the human need for categories than with any hard biological reality. Where exactly the bird begins is partly a choice, a decision about which features to privilege in the definition. The feathers are present long before anyone we would call a bird appears. The wishbone is present in many non-avian theropods. The air sac system is present in the sauropods and the theropods alike. The forward-facing eyes and the enlarged visual cortex appear in the Archaeopteryx. The warm blood, or something close to it, may have appeared in the theropod lineage long before flight. The bird, in some sense, assembles itself gradually from parts that were present before any bird existed. The lagoon is dark now, the reflection of the sky almost indistinguishable from the sky itself in the failing light. The Archaeopteryx is still. Its dark feathers are almost invisible against the dark of the tree. If you were not looking for it, if you had not watched it settle onto that branch an hour ago, you would not know it was there. Somewhere in the low trees on the far shore of the lagoon, another Archaeopteryx calls. The call is not a bird song. It is something rougher and stranger, something with the rasping quality of a reptile and the tonal variation of something that is becoming more than a reptile. The Archaeopteryx in the tree you are watching hears it. The head tilts briefly, then resettles. The lagoon reflects the first stars. The ancient, almost bird is still in the ancient, almost darkness, at the edge of what will eventually be an entire sky full of wings. The Jurassic night is complete now, not the partial dark of a modern city night, or the cloud-softened dark of a suburban night, or even the starlit dark of a rural night in the modern world. This is a darkness without precedent in the world, you know, a darkness in which the only sources of light are the stars and the moon, and the faint bioluminescence of the fungi that grow on the rotting logs of the forest floor, a blue-green phosphorescence so faint you would have to hold very still and let your eyes adapt fully before you could see it. Everything else is dark. And the stars. The stars in the Jurassic sky are overwhelming. You have to understand the absence of light pollution to understand what the night sky looked like to any animal alive before the first fire was lit. There is no fire tonight. There is nothing that produces light except the universe, and the universe is extravagant with it. The Milky Way is not a faint smear above the horizon, but a structure, a band of light so dense and varied that it has texture, cloud-like concentrations and darker voids and individual stars that are bright enough to cast faint shadows on the pale sand of the floodplain. The stars are not white. They are every color that a hot object radiates, from the cool red giants at one end of the spectrum to the blazing blue-white supergiants at the other. The sky is not black. It is dark blue at the zenith and lighter at the horizon. And across it the Milky Way sprawls in a brightness that no modern sky in any inhabited part of the world can replicate. The constellations are unrecognizable, the slow drift of the stars relative to each other over millions of years, the proper motion that accumulates too slowly for any human lifetime to measure, but that over geological time completely reorganizes the star patterns, means that the shapes you have been taught, the dippers and the bulls and the bears and the scorpions, are not present in this sky. But if you spent long enough watching, if you were an animal whose survival depended on navigating by the stars, as many animals do, you would find different patterns, equally reliable, equally true, equally useful for knowing which direction the predator came from, which way the water lies, how long until dawn. The sounds of the Jurassic night are different. The ree and the recorder. The daytime insects are mostly quiet now, sheltering in bark and leaf and soil. The night insects have taken over. The ancestors of crickets beginning their stridulation in the grass, free ground cover, the beating wings of large moths, searching for the conifer cone scales that carry the specific chemical signatures that evolution has tuned their olfactory systems to detect. Something in the high canopy makes a sound that is difficult to categorize, a repeated low note that might be the territorial call of a nocturnal reptile, a sound that has no analogue in the modern world and would not be recognized as biological if you heard it in a recording without knowing its source. The small mammal that slept through the afternoon under the root is awake. It emerged from the burrow at a precise moment, a moment determined not by any visible change in the environment but by an internal clock, a circadian rhythm calibrated over millions of generations to the timing of night in this latitude at this season. The clock said go. And it went. Emerging snout first from the burrow entrance, whiskers extended into the air above the leaf litter, to read whatever chemical information the night air is carrying. The air tells it several things. That the large theropod that paused near this spot in the afternoon has moved north. That there are insects active near the stream to the east. That nothing is immediately present that smells dangerous in the specific ways that the small mammal's deeply ingrained alarm system recognizes as danger. It moves through the forest floor in a way that is fundamentally different from the movement of the daytime lizards. Where the lizard moved in rapid, short bursts, covering ground and then freezing, the mammal moves in a continuous fluid motion, its body low to the ground, the large eyes held forward, the whiskers making constant contact with the objects it passes between and under. It is not fast by the standards of the daytime world. It is thorough. It investigates. It tests surfaces with its nose and sometimes its tongue. It communicates with its environment in a medium that the visual dominant world tends to undervalue: chemistry. The mammal finds a beetle larva under a partially decomposed piece of bark and eats it. The process is quick and efficient. Then it moves on, following a gradient of smell toward the stream, where the mud at the stream's edge holds a concentration of invertebrate life that is denser and more accessible than anything in the dry forest floor. Worms, freshwater crustaceans that the seasonal flooding brings from the floodplain and that persist in the mud for weeks after the water retreats. The small mammal hunts these with its nose and its digging forepaws, and eats and moves and eats again, maintaining the elevated metabolic rate that its warm-bloodedness demands by continuously converting food to heat and movement. Elsewhere in the forest, other nocturnal animals are moving, a group of small lizard relatives. Sphenodon, like animals that are less lizard and more something else, something older, something that belongs to a lineage called the Rhynchocephalia, that currently shares the land with the lizards, but will eventually lose out to them in every habitat except the islands of New Zealand, where the modern tuatara, the living representative of this ancient lineage, still exists in the darkness of its island forest, much as its Jurassic ancestor exists in this darkness tonight. These animals are slower moving than the daytime lizards, their cold-blooded physiology keeping them at a steady minimum temperature rather than the fluctuating extremes of a creature dependent on the sun, and they hunt at night in the patient, methodical way of animals that do not expend energy on speed they do not need. In the canopy, something moves. The sound of it is specific and close. A rustling in the upper branches of a large conifer, 40 meters to your north. Followed by a pause, followed by the sound of something rearranging itself, and then quiet. It is probably a small gliding reptile, finding its overnight position, adjusting its grip on a branch at the level of the canopy where the warmth of the day persists longest in the cooling air. Or it is something we have not yet found in the fossil record, something that lived and moved and died in the upper canopy of the Jurassic forest, and whose bones were never preserved in the sediment-depositing environments where most fossils form, because the canopy is not a sediment-depositing environment, because things that die in the canopy usually fall to the forest floor and decompose long before sediment can cover them. The gaps in the fossil record are a kind of darkness of their own. We know the Jurassic through the animals that lived near water, near floodplains, near lake shores and lagoons, in the environments where sediment is laid down and where bones are most likely to be buried before they decompose. The animals of the upper canopy, the animals of the deep interior desert, the animals of the high-latitude forests that existed but rarely preserved their dead, those animals are largely invisible to us. The Jurassic is fuller than we know, richer in life forms than the fossil record shows us, because the fossil record is a record of the places where preservation was possible, and preservation requires the particular collaboration of death and sediment that most environments, including the most species-rich environments, do not provide. The moon rises over the eastern ridge. It is slightly larger than the moon you know, the moon you have seen every month of your life, because in the Jurassic period the moon is closer to the Earth, its orbit having not yet fully expanded to the distance it will eventually reach. The tidal forces it exerts are therefore slightly stronger, the tidal bulge in the Sundance Sea slightly more pronounced, and the light it throws, the reflected sunlight that makes the moon the second brightest object in your sky, is slightly more intense than the moonlight you know. The forest floor under the moonlight is transformed. Where everything was darkness, there are now patches of silver light where the moonlight has found gaps in the canopy, circles and rectangles of illumination on the needle-covered ground. In these patches, the dew that has formed on the fern fronds catches the light and turns each frond into a constellation of tiny points. The stream, always talking, picks up the moonlight on its rippled surface and moves it in constant, slow patterns. The cycad fronds cast sharp shadows. The small mammal has returned to the vicinity of its burrow, but has not re-entered it. It sits just outside the entrance, its nose working the air, its large eyes oriented toward the patch of moonlit ground to the east, where a very large moth is moving between the root buttresses in the unhurried searching pattern of an animal looking for something specific. The mammal watches the moth with the particular quality of attention that a predator applies to prey when the prey is moving, but the predator has not yet committed to pursuing it. The waiting has its own quality, a tension in the small body, a readiness. The moth lands. The small mammal moves. It is quick, quicker than you would expect from something that has been moving with such measured slowness through the forest floor. The spring from stationary to full speed is nearly instantaneous, a burst of warm-blooded energy released all at once, and the gap between the burrow entrance and the moth is closed in a fraction of a second. There is a brief commotion in the leaf litter, then stillness, then the sound of the mammal eating. The Jurassic midnight carries all of this. The calls of the nocturnal reptiles and the scrape of small claws on bark, and the moth populations moving through the silver and shadow of the moonlit forest, and the deep, undying sound of the stream, and the breathing of the large animals resting in the valley below. It carries the smell of resin and decay and wet fern, and the animal warmth of the sleeping Stegosaurus in the valley, and the smell of the sea carried inland on the night breeze from the distant shore of the Sundance. The night is long. In the Jurassic, at this latitude, the summer nights are shorter than the winter nights, because the Earth still turns, the physics of its axial tilt unchanged by the change in what lives on its surface. But the night is complete. It is full. It is the night that covers everything that the day has shown you, the forest and the valley and the shore and the deep water, and the Archaeopteryx asleep in its tree above the lagoon and the sauropods, resting somewhere in the northern forest and the Allosaurus. Wherever the Allosaurus is tonight, its hollow bones light in the dark air. The mammal is back in its burrow. The moth is gone. The moonlight continues its slow progress across the forest floor as the moon rises higher, and the shadows that were sharp becomes slightly less sharp as the moon reaches the angle where the light diffracts through more canopy, and the dew on the ferns catches the light at a different angle and turns from silver to a dimmer, diffused grey. Everything sleeps or rests or hunts in silence. The world is very old and very quiet and very fully alive. The Morrison Formation does not announce itself. It is simply there, below everything, accumulating, layer by layer, season by season, flood by flood. The sediment that will eventually preserve this world in stone is being deposited in the floodplains and the river channels and the ancient lake beds that dot the interior of the continent. Red mudstones from the periods between floods, grey siltstones from the flood events themselves, pale sandstones from the river channels that meander across the floodplain, changing course every few decades, abandoning one channel and establishing another with the casual permanence of something that is not working toward any particular geography. The Morrison Formation will eventually extend across what will be, in the far future, Utah, Colorado, Wyoming, Montana, New Mexico, and several neighboring states, a layer of late Jurassic sediment up to 200 meters thick in places, a geological document that has taken 20 or 30 million years to write, and that will preserve more dinosaur species than any other sedimentary formation yet found on Earth. The bones it contains, when it is eventually studied and reported and argued about and revised, include at least 70 distinct species of dinosaur. 70. In a single geological formation, this is not a random accumulation of the dead. It is a record of an ecosystem so productive, so various, so deeply stocked with life, that even the improbable chance of preservation has generated, across millions of years and millions of deaths, an archive of extraordinary richness. The rain comes in the night. You have been asleep, or resting at the edge of sleep, and the first thing you notice is not the rain itself, but the change in the sound of the forest. The insects go quiet. The stream changes its voice, adding a lower register to its usual notes. And then the rain is on the canopy above you, a sound you have heard before in the past days in this forest, but not like this. Not with this weight and this density, not with this quality of arrival that does not feel tentative. The monsoon, the full monsoon, not the retreating edge of it that produced the rain of the past weeks, but the return of the weather system from the coast, refreshed, carrying more water than it released on the way inland, coming back inland from the distant Sundance seashore on a pressure gradient that has been building for 3 days. It arrives in the night without warning, except the warning that the insects clearly received before you did. The sound of heavy rain on the conifer canopy is something between a roar and a hiss, a continuous white noise of extraordinary completeness that fills every frequency of the audible range and some above and below it. You cannot hear the stream anymore. You cannot hear the wind, though the wind is certainly present, driving the rain in sheets through the upper canopy. You can see, in brief flashes when the lightning fires, the ferns being pressed horizontal by the falling water, the surface of the visible ground beginning to reflect the downpour, the water that was formerly absorbed by the needle mat now running in thin sheets across the surface because the needle mat is saturated and can absorb no more. The lightning here is extraordinary, not the brief flicker of the convective thunderstorms you know from your own climate, but the long, branching, ground-striking strokes of a Jurassic monsoon cell, each stroke lasting long enough to actually illuminate the forest for a genuine instant, long enough to see the rain as individual drops rather than continuous sheets. In these moments of illumination, you can see the old-growth forest around you with a clarity that the daylight does not provide, a clarity that comes from the specific blue-white of lightning, which renders the green of the ferns as near black and the pale underside of the conifer needles as silver and the standing water on the needle mat as a mirror. The lightning strikes a tree, not a very close tree, perhaps 200 meters to the north, and the sound of it arrives as a crack followed immediately by a deep, resonant thud that you feel in your sternum as much as you hear in your ears. In the seconds that follow, in the gaps between rain pulses, there is the smell of ozone and then, faintly, the smell of burning wood. The struck tree smolders for a moment, the wet bark preventing open fire, the fire chemistry occurring inside the wood rather than on the surface. Whether it will actually burn when the rain stops depends on how deep the damage went and how long the dry season that follows will be. Many of the fossilized charcoal deposits, the fusane, found in Morrison Formation rocks began exactly this way: a lightning strike, a smoldering tree, a dry season that allowed the fire to spread and consume and carbonize the wood before the next monsoon arrived to bury the evidence in a fresh layer of silt. The trees of the Morrison Formation burned seasonally. This is one of the more unexpected facts in the story of the Jurassic Morrison ecosystem. Evidence of ancient fires, in the form of fossilized charcoal found within the sedimentary layers, appears throughout the Morrison Formation record. The Jurassic world was not perpetually green and wet. It had seasons. It had a monsoon that lasted several months, and a dry season that followed it. A dry season during which the accumulated plant material of the wet months became fuel, and lightning from the beginning dry season thunderstorms was the ignition source. The fires were not catastrophic. Not the landscape-level fires of the modern American West during drought conditions. They were seasonal forest fires, burning patches of the understory, clearing the dead material, releasing the nutrients locked in the burned wood back into the soil, creating open areas that new growth quickly colonized. The dinosaurs of the Morrison knew fire. Not as a concept, obviously, not with any understanding of its chemistry or its causes, but as a sensory experience, certainly. The smell of smoke was a specific signal in the Morrison environment, a signal that large animals responded to by moving away from it, the same response that modern large animals display, a response that requires no learning because it is encoded in the olfactory alarm systems that evolution has refined over millions of years of selective pressure from exactly this kind of event. The rain intensifies. You are already wet. Now you are more thoroughly wet, a distinction that matters somewhat less than you might expect, because the night air is warm enough that the water on your skin is the same temperature as the air around it, and the boundary between inside and outside feels less meaningful than it normally would. The needle mat beneath you is cold now, the water having driven the day's warmth out of it, and you can feel the difference between the cold, wet ground below and the warm, wet air above, your body held between the two temperatures in the specific way of something alive in a world that is not particularly concerned with its comfort. The flooding begins at the low points of the forest floor first, in the hollows between root buttresses where the water collects before it has anywhere to go. You watch a hollow near you fill from a thin sheet to an inch of water to 5 inches of water in the space of perhaps 20 minutes. The surface of this impromptu pool catching the lightning reflections and shaking them in the rain. Something moves in the pool, a small frog or frog-like animal that appeared there without your noticing its arrival, simply present in the water once the water was present, as though it materialized with the rain. It will breed here if the pool lasts long enough. Hundreds of eggs, perhaps thousands, deposited in the warm, shallow water, developing rapidly through the tadpole stage in the brief window before the dry season begins and the pool evaporates. The rivers outside the forest are doing something more dramatic. The permanent river that drains the Central Valley, the one that threads through the Stegosaurus Valley and carries the floodplain's red silt eastward to the Sundance Sea, has been rising since the first rains of the monsoon arrived. Now, in the full intensity of the monsoon's return, it has left its main channel and spread across the floodplain in the way that Morrison rivers did regularly, the way that the geological record shows them doing in the patterns of ancient river channel deposits and overbank silts that alternate in the Morrison Formation rocks. The spread water moves slowly across the flat floodplain, carrying the red silt and the dissolved minerals and the organic matter from the flooded forest edges, and it is this slow, silt-laden water that will eventually deposit the layers of sediment in which the bones of the animals that die here will be preserved. Bone preservation in the Morrison happened mostly in this way. An animal died, near water, in the wet season, and the seasonal flood buried the bones under a thin layer of silt before the insects and the scavengers and the bacteria could fully disperse them. Then the next flood brought another thin layer, and the next, and slowly, across decades or centuries, the burial deepened and the chemical conditions changed, and the calcium phosphate of the bone began to be replaced by minerals from the surrounding sediment, and the fossil formed. The formation of a fossil is an improbable event. For every Morrison Formation dinosaur whose bones are preserved in stone, there were hundreds or thousands or millions whose bones decomposed completely, scavenged and scattered and consumed by the various mechanisms of decay until nothing remained. We see the survivors of this process, the few who happened to die in the right place at the right time in the right season, to be caught by the silt before the silt's opportunity passed. The Jurassic is far larger than its fossils. Its full complement of species is a number we cannot access directly. The fossils are evidence of its richness. The fullness of it is beyond the evidence. The rain continues through the night. If anything, it intensifies toward what you would estimate is the middle of the night, the rainfall reaching a density that produces a solid sound, a roar that the forest translates into something lower and more complex by the time it reaches you at ground level. The lightning is less frequent now, the core of the storm having moved east over the floodplain, but the thunder still comes, delayed by the distance, low and long-rolling. You realize, in the way that realizations come in the middle of long rainy nights, not as insight but as slow arrival at something already true, that this rain is the Morrison Formation. This rain, these specific drops falling on this specific forest floor, will eventually become the mudstone layers that will preserve whatever dies near here in the next several months. The atoms of the rain, the hydrogen and the oxygen of it, will be part of the rock that someone in an unimaginable future will chip at with a geological hammer and look at with a hand lens and eventually identify as late Jurassic Morrison Formation sediment, somewhere in what will be the American West. The rain does not care about this. The rain is simply rain, falling because the physics of the atmosphere in this season at this latitude produce this outcome. It has been falling on this ground for millions of years before tonight and will fall on it for millions of years after. And the forest, which has been in this rain before, settles under it with the patience of something very old and waits for the morning. The Jurassic does not know it is ending. This is not a metaphor, or not only a metaphor. The Jurassic Period, as we define it, ends approximately 145 million years ago, a boundary drawn in the geological record, by subtle changes in the fossil assemblages that the period contains and in the physical chemistry of the rocks. The boundary is one of the least dramatic of the major geological period boundaries. There is no mass extinction event at the Jurassic-Cretaceous boundary, no asteroid, no flood basalt eruption, no catastrophic collapse of ocean chemistry. Life moves across the boundary with no particular awareness that it is crossing one. What actually happens at the Jurassic-Cretaceous transition is a gradual, overlapping rearrangement of species. Some genera that were common in the late Jurassic become rare or absent in the early Cretaceous. New genera appear. The overall composition of the large animal fauna shifts. But the shift is not a break. It is a continuation. Many of the major dinosaur groups cross the boundary intact, dinosaurs very similar to the ones in the Morrison ecosystem, continuing into the Cretaceous and diversifying further there. The transition from Jurassic to Cretaceous is more like the transition from one chapter to the next than from one book to another. This is worth holding, because the human tendency when thinking about geological time is to think in events, in moments, in the dramatic punctuation marks of mass extinction and asteroid impact and volcanic catastrophe. These events happened, they are real. But the majority of the geological record is not events. It is intervals between events. Long, calm stretches of geological time in which the world changes slowly by the accumulation of tiny changes, in which the composition of ecosystems shifts not in catastrophic jumps but in the slow drift of evolutionary response to climate, to sea level, to the continuing movement of the continents. The late Jurassic, the Morrison period, is one of those calm intervals. It lasts perhaps 20 or 30 million years, which is a long time in any reckoning. And during those millions of years, the basic structure of the ecosystem is maintained. The same large sauropods, the same large theropods, the same small mammals in the understory, the same pterosaurs in the sky. Individual species come and go, the slow background rate of extinction and speciation continuing through the whole interval. But the architecture of the ecosystem, the pattern of who eats what and what eats whom and which niche is occupied by which kind of animal, that architecture persists. It persists because it works. This is the most important thing to understand about a long-lasting ecosystem. It is not stable because of inertia, not preserved by the past's momentum. It is stable because it is functional, because every piece of it is doing something necessary, because the web of relationships between its members has been tested by time and has passed. The Allosaurus and the sauropod and the Stegosaurus and the small mammals and the pterosaurs and the insects and the ferns and the conifers form a system that feeds itself and maintains itself, and adapts to seasonal variation without destabilizing, a system robust enough to persist for geological intervals. Here, on this morning after the rain, in the dripping forest, the system is going about its business. The morning birds, or near birds, are doing their after-storm survey of the canopy for insects displaced by the rain. The stream is high, red-brown and fast, carrying the night's accumulated runoff east toward the floodplain. The Stegosaurus in the valley have risen and are moving through the new growth that the rain has encouraged in the areas of the valley floor that were already wet. The small mammal is back in its burrow, full from its night hunt, sleeping through the warming morning with the contentment of a creature that has done exactly what it was designed to do. There is a remarkable fact about geological time that becomes more remarkable the longer you sit with it. The Earth is approximately 4,500,000,000 years old. Complex, multicellular life has existed on it for perhaps 540 million years since the Cambrian explosion of animal body plans. The Jurassic Period lasted approximately 56 million years. The entire duration of the dinosaurs, from their first appearance in the Triassic to the extinction of the non-avian lineages at the end of the Cretaceous, was approximately 165 million years. Human civilization, from the first cities to the present, is approximately 10,000 years old. The Jurassic lasted more than 5,000 times longer than all of human civilization. The dinosaurs were here, in total, for more than 16,000 times longer than we have been. If you mapped the history of complex animal life on Earth onto a single day, with the Cambrian beginning at midnight and the present moment at the following midnight, human civilization would occupy the last 2 seconds. The Jurassic would occupy approximately 5 hours. The dinosaurs would be present for about 9 hours. And the first complex animals, the Cambrian creatures, would appear at midnight, and the sea would be full of them for the entire day before a single land animal took its first steps in the afternoon. This is not a thought designed to make you feel small. It is a thought designed to help you feel the texture of deep time, the way that what we call history is compressed into a window so narrow that the geological periods before it are almost incomprehensible in their duration. The morning you are in right now, after the rain, with the forest dripping and the stream high and the sauropod footprints filling with red water in the valley below. This morning is one morning in tens of millions, one iteration of a pattern that has been repeating since before the Morrison Formation began accumulating, and will repeat until long after it stops. The morning after the monsoon rain in the Jurassic forest has a specific character that you might spend a lifetime trying to describe, and not quite succeed. The air is clean in the specific way of air that has been thoroughly washed. Every particle of dust and pollen, and the 1,000 microscopic things that float in warm, dry air, having been driven to the ground by the weight of the rain. What remains is air that is mostly air, humid and warm, and carrying only the immediate chemical signals of the wet environment. Resin released by the rain, soaked bark, the specific green smell of crushed and wet fern fronds, the earthy smell of the saturated soil. It is an air that has no impurities and no history, air that began raining as the sea and arrived here as itself. The light through the dripping canopy has a quality particular to wet mornings, a quality of diffusion, too of light, that has been scattered by the water on every leaf and needle until it arrives at ground level as something soft and even, without the hard shadows of the dry day, without the strong directional emphasis of sunlight coming from a specific angle. Everything is equally lit in this light, equally visible, equally present. The forest floor is detailed. In a way it is not always detailed. Every fallen needle and every small stone and every mushroom cap, visible in the same clear wash of post-rain morning light. Something large walks through the shallow floodwater that has accumulated in the low areas of the valley floor. You cannot see it from here, but you can hear it, and the hearing is enough. The distinctive sound of large feet in shallow moving water, a repeated wet impact followed by a pause followed by another impact, the rhythm of a large animal picking its way through unfamiliar footing with the careful attention of something that prefers dry ground and has found itself in flooded ground and is proceeding with the dignity appropriate to the situation. You find yourself thinking about what the world will look like when this morning is gone. Not merely when this day is gone, not when this year or this century is gone, but when the entire Jurassic is gone, when the animals that populated it have been replaced by their descendants or by the descendants of the lineages that outlast them, when the forest that surrounds you has been replaced by different forests and then returned and been replaced again. The thought has the quality of a very long exhalation. A thought that takes in more than the lungs can hold and lets it go slowly. The world will change. It always has. The Cretaceous will bring flowering plants, and with them the first bees and butterflies, and with them the restructuring of the plant-insect relationship that will eventually produce the modern world's extraordinary diversity of both. The Cretaceous will bring new dinosaurs, tyrannosaurs and ceratopsians and hadrosaurs in the north, a different fauna from the Morrison but equally successful, equally various. And then, 66 million years from this morning, an asteroid will arrive from space, and everything will change with a suddenness that the Morrison ecosystem, with its deep geological patience, could not have accommodated. But all of that is very far from this morning. Here, now, the forest is dripping, and the stream is high, and the small mammal is sleeping in its burrow, and the sauropod is picking its way through the floodwater with unhurried care, and the world is exactly what it has been for millions of years, and will be for millions more. The geological boundary between Jurassic and Cretaceous, when it comes, will not announce itself. It will not feel like an ending from inside it. It will feel like another morning after another rain, another morning in a sequence of mornings that extends in both directions further than any mind can hold, each one complete in itself, each one belonging entirely and without remainder to the world that produced it. The world does not know it is being preserved. The Morrison mud that fills the sauropod's footprint this morning does not know it will become stone. The small fly that lands in the fresh resin on the wounded conifer does not know it will become amber. The morning does not know it will become a chapter in a story told by minds that will not exist for 150 million years. It is simply morning. After rain. In the Jurassic, the conifer canopy catches the rising light and holds it for a moment before letting it fall through to the dripping ferns below. And the world goes on with what it has always been doing. The afternoon of the last day you will spend in the Jurassic world has come around in the way that all afternoons come, with the warmth settling into everything that has weight, and the light beginning its slow withdrawal from the sky's zenith. The forest has dried since the monsoon rain, the needlemat drinking in the warmth it lost in the night, the fern fronds lifting from the horizontal press of the downpour to their usual upright posture, reaching again for the filtered light that falls through the canopy. You have been here long enough to know this forest in the way you know a place that you have slept in and woken in and watched through several weathers. The Jurassic has been patient with you. It has continued its business around you without interruption, the ecosystem running on its geological timescale with the same indifference to your presence that it has maintained since you arrived. The sauropods have moved through the northern forest without noticing you, or if noticing, without caring. The Allosaurus at the stream did not eat you, whether out of indifference or calculation, or simply because a stationary primate is not a prey type in any behavioral template this animal carries. The small mammal under the root has been your closest companion in some ways, though it does not know this and would not find the description meaningful. The afternoon light in the Morrison forest at the very end of the Jurassic period is the same afternoon light that has fallen here for 20 or 30 million years. It enters the canopy at the angle dictated by the season and the latitude and the declination of the sun, and it falls through the conifer needles and the cycad fronds and the tree fern canopy in the same patterns it has always fallen. The long bars of light on the forest floor, the circles and ellipses of illumination that shift position through the day as the sun moves, the deep shade under the most densely canopied areas where the light is reduced to a general dim green glow that is enough for the shade-adapted plants, but not enough for the sun-adapted ones. All of this is unchanged from the first morning you arrived. The world is very old, and it does not show its age in the way that old things in the human world show their age. There is no weathering of the kind that produces ruins. There is no accumulation of the obsolete. The forest replaces itself continuously. Old trees falling and new trees filling the gap. The individual organisms of the ecosystem cycling through birth and death and decomposition on their various timescales, while the architecture of the ecosystem itself persists. An old forest looks young because it is always in the process of being young, always growing, always filling the light that falls into gaps with new growth. What will change, eventually, is not the forest's appearance, but its composition. The first flowering plants are already latent somewhere in the Jurassic world, already evolving in some population of magnolia-like plants in some environment we have not found in the fossil record. Their appearance in the early Cretaceous, as sudden seeming in the fossil record as any evolutionary event, though of course not sudden at all in the actual time of its occurrence. When the flowering plants appear and spread, they will change the visual quality of the forest fundamentally. Color will arrive in the form of petals. Fragrance will intensify as the chemical signals that attract pollinators become elaborated into what the human nose will eventually experience as scent. Fruit will appear, the reproductive strategy of enclosing seeds in nutritious packaging that animals will eat and carry and deposit elsewhere, a strategy so successful that it will eventually cover most of the world's land surface with the descendants of those first flowering plants. The Jurassic forest has none of this. What it has is the deep, resinous, green and earth smell of a world before flowers, a smell that is older and simpler, and in its own way as complete as anything that will come after it. You breathe it in on this last afternoon, this smell of the oldest world you will ever visit, and you try to hold it, and you cannot hold it, and you let it go. There is a movement in the western sky, above the ridge that marks the boundary between the valley and the higher ground. The pterosaurs are flying again in the late afternoon thermals, their silhouettes against the pale western sky precise and unhurried, the long tails of the Rhamphorhynchus making them unmistakable even at distance. They are doing what they do every late afternoon, rising on the thermals, hunting the insect emergencies, managing their aerial territory with the patient efficiency of animals that have been doing this for millions of years and have refined the practice to a simplicity that looks effortless. The sauropod vibration is present again in the north. You have become so accustomed to it, this low periodic pulse in the earth, that you notice its absence more than its presence. It has been absent for several hours, since before the afternoon began, and its return now tells you that the animal that produces it has come back from wherever it went in the middle of the day, come back to the forested northern slope, where its browsing path crosses the ground above you, and its footfalls can still be felt through the needle mat and the stone beneath it. The footfalls come at their usual interval, the rhythm so regular that after a while it becomes like a clock, a biological clock running at the pace of something that weighs several tens of metric tons and sees no reason to hurry. A Jurassic afternoon in the last part of the Jurassic period. The last part is a relative term. It covers several million years. Within those millions of years, this afternoon is one of uncountable trillions of afternoons, each one like this one in its essentials. The light and the heat and the animals going about their business, and each one different in its details, the specific angle of the light, and the specific animals visible, and the specific sounds carried on the specific afternoon air. Every afternoon in the Jurassic is unique. Every afternoon in the Jurassic is the same. This is the quality of deep time that is hardest to maintain in the mind. The repetition and the uniqueness are both true simultaneously, and holding them simultaneously requires a kind of attention that the human mind, designed for the time scales of a human life, does not naturally sustain. We keep collapsing the Jurassic into a moment, a snapshot, one image of one afternoon in one forest. But the Jurassic is not a snapshot. It is a duration. It is 56 million years of afternoons like this one. 56 million years of the same sun falling through the same kind of canopy onto the same kind of forest floor. 56 million years of the same sauropod rhythms in the same kind of floodplain and the same pterosaur shapes against the same kind of sky. And none of them knew it would end. That is perhaps the most human thought available in this inhuman landscape. None of them knew. The sauropod whose footfalls you can feel right now will not know, when the Jurassic ends, that an era has ended. The Cretaceous will begin the following morning, and the morning after that will look exactly like this morning, and the same animal will be in the same forest doing the same thing because nothing has happened that would tell it otherwise. The geological boundary between the Jurassic and the Cretaceous is a line we draw, not a line that nature drew. Nature only drew the actual moments, one after another, without categories. The sun is lower now, and the forest's long, late shadows have claimed the valley floor and begun to climb the eastern slope. The Stegosaurus in the valley are silhouettes again, as they were last night. their profiles against the still bright eastern sky. They are feeding at the valley edge where the sun still reaches the cycads, taking advantage of the last warm light before the evening cools the ground and the animals settle into their overnight posture. You watch the sun's retreat from the forest floor. It withdraws from the easternmost areas first. The shadow of the western ridge, advancing across the valley, and the forest edge at the pace of shadow, which is the pace of the turning earth, too slow to see but fast enough that if you look away for 10 minutes and look back, the boundary of shadow has moved measurably across the ground. The conifers on the western slope still hold the full warmth of the late sun, their bark heated through the afternoon to a temperature slightly above the air, radiating that heat back as the air cools. The resin smell is strongest at this hour, released by the warm bark, hanging in the still air of the forest interior, where the evening breeze has not yet reached. It is a smell that carries the whole afternoon in it, the whole long warm afternoon of the Jurassic, with its sounds and its shadows and its slow biological rhythms. If you could take the smell with you, carry it out of this forest and into the world that waits in the future, it would be a better record of this place than any fossil, any rock, any geological document. But smells do not fossilize. They exist only in the moment of their occurrence, and when the moment ends, they end. The last light catches the top of the tallest conifer to the west of you, the very tip of its crown, a point of gold against the sky that is beginning to turn the colors of evening. The tree has been here for 150 years. It will be here for another 100 years if nothing breaks it, another century of reaching toward the light, with the same patience with which it has been reaching since it germinated from a cone in a wet hollow in the aftermath of a previous monsoon season. It does not know it is beautiful. It does not know it is ancient. It simply reaches. The gold at the top of the conifer fades. The sky completes its evening gradation, and the first stars appear in the east. The same stars that appeared on the first night. The same positions, the same colors, the same astronomical permanence that makes the forest and the valley and the Jurassic itself seem brief by comparison. The sauropod footfalls in the north slow and then stop. The large animal has found its overnight position, settled into the forest floor with the vast weight of itself and the enormous slow breath of itself, and it rests. The Stegosaurus in the valley have lowered themselves to the ground, the plates tilting with the bodies settling, catching the last of the sky's reflected light. The small mammal under the root is beginning to stir, turning in its burrow, its internal clock registering the cooling of the air above as the signal to prepare. The Archaeopteryx at the lagoon shore, many miles to the east, is asleep in its tree above the still water. Everything that the Jurassic is, every organism, and every relationship between organisms and every atom of rock and water and air that the period contains, is present in this moment, going about its business in the way it always has, without knowledge of beginning or end. The sky is very deep. The stars are very far. The world is very old, and you are here in it, resting on the ancient needle mat of an ancient forest, warm in the warm air of the warmest era the planet has known, breathing the oldest clean air available to any mind. Let the forest hold you. Let the deep time hold the forest. Let the dark come. Thank you so much for watching. If you enjoyed this journey through the ancient Jurassic world, please consider leaving a like and subscribing to the channel. It really helps us continue making more content like this. Anyways, see you in the next one. The dark is here now. The forest is breathing around you in the slow, enormous way that forests breathe. The trees absorbing the cooling night air through their bark and their needles and releasing the stored warmth of the day back into the dark. The smell of it is the same smell it has been all day, all night, all through your time in this world. Resin and earth, and the distant mineral smell of the stream. Let your body settle into the ground, into the needle mat that is soft and deep and has been here for as long as anything nearby can remember. The weight of you belongs to the earth, the way the weight of the trees belongs to the earth, pressed into it by the same gravity, held by the same patience. The sauropod is breathing somewhere in the northern dark. You cannot hear it from here, but you know it is there, that enormous breath rising and falling in the dark forest. The great lungs moving air through the bird-like air sac system that has been working without rest since the animal was born, breathing in, breathing out. The same rhythm as your own breath, only slower, only larger, only more ancient. Let your breath slow to match the forest's breath. In and out. The stars are above the canopy, though you cannot see them through the trees. They are there the way they are always there, in the specific positions they occupy in this era of geological time, before the slow drift of their proper motion has moved them to the positions you know from your own life, your own nights, your own window onto the sky. They are the same stars. They are older versions of the same stars, burning in the same nuclear way, casting the same light across the same darkness toward the same warm planet beneath. In and out. The stream is talking to itself. It has been talking to itself since before you arrived, and it will continue after you have gone. After the Jurassic has ended, and the Cretaceous has followed it, and the asteroid has fallen, and the mammals have risen, and the ice ages have come, and the cities have grown, and the lights have spread across the night until no dark remains, except the dark in the rooms where people sleep. This dark, this Jurassic dark. This is the dark that existed before all of those things, and it exists now, and in it the ancient world rests. Let your thoughts slow. Let the images of the day, the sauropod's neck against the morning sky, the Allosaurus at the stream, the Stegosaurus settling in the valley, the Archaeopteryx on its branch above the lagoon mirror, let them come and let them go, the way clouds come and go across the face of the moon. You are resting in deep time. In the oldest world available to any imagination, in a world that is still in the process of making itself, patient and enormous and entirely unhurried. In and out. The needle mat is soft. The air is warm. The world is 150 million years old. Sleep now. The Jurassic will be here when you return. Where in the world are you listening from tonight? And what time is it where you are? I am always curious about that. Leave it in the comments. And if you have a prehistoric world you would like us to visit next, let me know. The ancient Earth has many rooms, and we have only just begun to explore them. Good night.